So first speaker today is Hiroshi Kunitomo from Kyoto. He's going to revisit type 2 superstring field theory. Kunitomo-san, please.
Okay. First of all, I would like to thank the organizers for organizing this string field theory workshop for this year in this worldwide COVID-19 pandemic situation. And I'd like to thank also, thanks for allowing me an opportunity to give a talk today. Okay. This is my title of my talk, and based on these references. Will freeze my. Sorry. And let me start with some brief introduction. Now, there are many, mainly three complementary, in a sense, complementary approaches of superstring field theory, and we have succeeded in completing at least classically superstring field theory for all these three approaches, except for the Sumino-Witten-like type 2 theory. This is the table of them. So in this talk, we first revisit the L-infinity algebra-based type 2 superstring field theory and propose a new construction method, which is an extension of the so-called symmetric construction given by Munich people, Knopf and Zacks for NSNS sector. Then we construct the Sumino-Witten-like axiom through the map, defining using the gauge product of the new construction. Okay, let me start with some brief summary of what is the basics of the type 2 superstring field theory. Now, the string field is in the small Hilbert space, but there are four components in the fourth, corresponding to the four sectors: Bouchard-Schwarz, Ramon-Bouchard, Ramon set. The string field has Gauss number 2 and Fisher numbers. The Fisher numbers is independently conserved with left moving sector and right moving sector. The Fisher numbers is -1 for next sector, and so on and so forth. The string field constrained by two kinds of constraints. The first one is a so-called cross string constraint, that because type 2 string is cross string. And the second one is extra constraint that restrict the super Gauss dependence of the super Gauss zero in the Ramon sector. And G and G inverse is defined by these operators using the projector onto the each component, and also the picture changing operators defined like here. Then if you expand each component of this string field in this restricted Hilbert space in the Gauss zero mode, it has a form of it has these forms. The gamma zero is the super Gauss zero mode, the bosonic Gauss zero mode. So in principle, the infinite power is allowed, but constraint restrict the dependence is just at most linear dependence. Here, so essentially that there are two components, phi and psi, for each component. These phi's and psi's correspond to the field and anti-field of the BB formulation in the gauge fixed basis respectively. And we also can define the symplectic form in the small Hilbert space by using the conventional BPZ inner product. And in the restricted Hilbert space, restricted by the constraint just mentioned before, has a form here, inserting the inverse picture changing operators that is asymmetric in the four sectors. But rewriting it in this phi and psi, that is just a skew symmetric form, just correspond to the field and anti-field. We also use an asymmetric form in the large Hilbert space, which is similarly defined to the small omega s. And we have, if phi 1, phi 2 is in the restricted space, omega L and omega S is related in this relation. And the n+1 string interaction is represented by some multilinear map from n strings Hilbert space to the one string Hilbert space, where this notation, which n is the space of the symmetrized tensor product, which is mentioned by the Olaf's lectures, which is defined, the element of this space is defined by this symmetrized tensor product. And we also identify the L1 is just a BRST operator. And if these multi-string products satisfy these relations, the first relation is called the L infinity relation, and the second one is a cyclic relation. Then it is called these three pairs called cyclic L infinity algebra. Okay, so if you have this cyclic L infinity algebra with appropriate Gauss and picture numbers for the type 2 theory, the action is given by this form. And this is invariant under this gauge transformation. And we assume, or we know that this Ln with appropriate Gauss numbers, but no picture number, can be constructed similarly to the bosonic closed string field theory. So we must find how to construct this Ln with appropriate picture numbers from those without picture numbers. We call those without picture numbers called bosonic L infinity. Okay, next issue is how to construct this L infinity, cyclic L infinity. We use the co-algebra representation, which was also represented by the lectures by Olaf Fong. That is the co-algebra acting the symmetrized tensor algebra. The formal sum of these or the powers. The co-derivation act in this symmetrized tensor algebra, which is defined by this action. The L infinity algebra is represented by a degree odd, we said -1 co-derivation, also the sum of this sum of this Ln satisfying this nilpotent relation. Okay, so next is how to construct L. Which the L with appropriate picture numbers is parameterized this form. Here the P and P bar is picture numbers, which has proper picture number of the vertex co-derivation is. And this subscript is represent matrix notation, which has only the diagonal elements, and the subscript after the slash is Ramon numbers, which is defined by number of Ramon inputs minus number of Ramon outputs. The left-moving Ramon number and the right-moving Ramon number is independently constructed. However, it is not easy to construct this cyclic L directly because the Ramon number is not invariant under cyclic permutation. Because the cyclic permutation changes the input and output. So instead, we consider another degree of co-derivation defined by this with a superscript 2R and 2R bar. That is that the cyclic Ramon numbers is defined by the number of Ramon inputs plus number of Ramon outputs, which is invariant under cyclic permutation. Okay, and suppose that in the large Hilbert space, this D defined by these relations is an L infinity algebra that is satisfying this nilpotent relation. Or equivalently, there are three mutually commutative L infinity algebras, which is defined by which is decomposed from this to the Gauss number and picture numbers. three mutually commutative L-infinity algebras. That is that these DC and C bar satisfy these relations. Okay, then if you have these three L-infinity algebras, then cohomomorphisms, that is called L-infinity morphism in the Holmes lecture, defined by this cohomomorphism, maps these three L-infinities to the L and the eta bar. Yeah, satisfying this simple relations. And also, the point is that also that this L has this form. The interaction part, in front of the interaction part, there are picture changing operator G, which gives this symplectic form of this form of the symplectic form in the action gives just like this symmetric form, cyclically symmetric form due to this prefactors. So we can show that if B, large B, this B is cyclic with this large Hilbert symplectic form in the large Hilbert space, then this small b is cyclic with respect to the small symplectic form in the small Hilbert space. And thus, this large L is cyclic with respect to this capital omega. Then that means that this cyclic infinity algebra is a desired algebra. That's the story. So now we have to explicitly construct this infinity algebra. Yeah, this nilpotent relation is equivalent to this, can be decomposed in these three relations, where the commutator with some superscript 1,1 or 2,1 and so on is defined by this project graded commutator with projecting the intermediate state to the each sector. So for example, that bracket 1,1 is defined by projecting the intermediate state to the Bouchard sector, and subscript 2,1 is defined by projecting the intermediate state to the Ramon-Bouchard sector, and so on and so forth. And we also introduced that to bracket 2,2 with some subscript x or x bar that defined by that projecting the intermediate state to the Ramon sector and also insert the picture changing operator x, and so on and so forth. Okay. Then if we define the generating function by these three parameters, S bar t, S and S bar counting that picture number of the picture number deficit of these P co-derivations, and P T counting that the picture number of the total picture number of the co-derivation. And we also that lambda and lambda bar is called the gauge product, the degree even co-derivation. And also for later use, we denote the gauge product restricted on the Nebuchadnezzar sector that plays an important role later. That means that this cyclic Ramon number to the 0,0 sector is denoted by lambda ns ns or lambda bar ns ns. Okay, if this generating function satisfies the differential equation, that is a bit complicated, but this form of the generating differential equation, then we can show that this relation hold, which reduces to the relation, this desired relation at S and S bar is equal to 0 and T equal to 1. Yeah, note that in the SNS sector, the differential equation, this a bit complicated differential equation, and the relation, this complicated relation reduced to those of the symmetric construction given by Munich group. So this now this construction is an extension of their construction. Okay, then we can show that this differential equation can be recursively solved under initial condition with that the picture number with no picture number sector is given by the bosonic string product by inserting the X0, X0, and X0 bar, and so on and so forth into bosonic product. So as to respect to cyclicity. Okay, then using B is given by the B001, we can obtain this desired L infinity as well. And then using the co-homomorphisms, we can obtain the desired L infinity. That the form that has this form. Okay, now consider the map to the Witten-like action. Yeah, and Ted pointed out that these 3 or 2 or 3 L infinity algebras characterize the string field theory. In particular, Matsunaga said that the L infinity triplet characterized the type 2 to superstring field theory. The basic triplet is given by eta bar, eta and eta bar is trivial L infinity, just nilpotent of A. The L is the one we can find now. This triplet gives this equation. And the first two, eta phi equals 0, and eta bar phi equals 0, that is a so-called constraint L infinity, named like that. This equation constraint that the string field phi is in the small Hilbert space. And the third one, dynamical L infinity, gives the equation of motion of the superstring field theory. Then co-homomorphism or L infinity morphism given by this let's see, ordered product, ordered exponent, first ordered exponential of the gauge product in the Nebuchadnezzar sector maps this basic triplet to some dual triplet like this. Here, before further consideration, this homomorphisms is non-trivial only in the NSNS sector. It maps phi as this form. Only the Nebuchadnezzar's component non-trivially map to the dual picture. And the other 3 components is invariant under this homomorphism. So for this dual multiplet, the 3 equations constraint L infinity given by constraint L infinity and dynamical L infinity have this form. Yeah, and the new constraint, this constraint can be solved by setting that by this identification. The Nebuchadnezzar sector, we introduce another field B, which is the NSNS field in the Witten-like formation, which has both number 0 and the picture number 0, 0, 0, 0. And the other 3 is invariant under this maps. So we just name another notation in psi and psi bar and sigma, just for distinguishing the which is the field in the which formulation. This G eta bar is the dual, so-called dual pure gauge field, which is constructed, explicitly constructed by Matsunaga-san, and have this form. We can solve some more Karpman equations order by order in this form, but perturbatively different obtained. Then the Witten-like action is given by this simple form where G is given by that G, this pure gauge configuration for the Schwarz-Muster sector. And we also extend one parameter, give the one parameter extension to the other three components. And this curly BT is the so-called associated string field, which is that we know that the form of the Schwarz-Muster sector, which is explicitly given by Matsunaga-san. And the other components have just this form, the derivative psi, derivative psi bar, derivative sigma, with some C0.
So you have 5 more minutes?
Okay.
5 minutes?
Then this action is invariant under the gauge transformation. This form, the gauge transformation is also mapped from the identity-based formulation. And but the gauge imbalance is extended because of that this map G is equal to GB. This map is not one-to-one, but redundant. This is invariant under some transformation of B that gives a extra gauge invariance in the Witten formulation. Okay, let me summarize and give some outlooks. In summary, we revisited the type of superstring field theory and propose a new construction method extending the symmetric construction for NSNS sector, which is given by the Munich group. And using gauge product of new construction, we give a map between string field of LFT-based formulation and Witten-like formulation and construct the Witten-like action. And that means that we fill the gap and completed the table of the three complementary formulations for the superstring field theory. So I think that at least classically, all the formulation is now completed. And we will I will give outlook. Then we are now turning a point that we can start the concrete analysis using superstring field theory. Of course, non-perturbative analysis, that classical solution, dualities, ADS-CFT, these Stanton, and so on and so forth. Not only the non-perturbative analysis, but also there are many perturbative analysis which is which cannot do which is only analyzed by using that string field theory. For example, the off-shell amplitude, calculating off-shell amplitude, infrared divergence, and so on. Non-renormalization theorem, and so on and so forth. And it is also interesting to quantify these actions, the gauge fixing problem, the loop homotopy algebra, quantum BB master action, and so on and so forth. And yes, we have still many remaining issues to study. Okay, that's all for all I want to talk today. Thank you.
Thank you. Thank you for the nice talk, Kunitomo-san. So any questions? Nathan?
Hi, thanks for the talk. I think the topic is extremely interesting. I want to understand just the quadratic and cubic term in the Never-Schwarz sector. Can you say, so the quadratic action, is it just something like phi q eta bar phi?
In the Witten-like action?
Yeah. I just want to understand the quadratic and cubic terms. That would be a great help to me.
In the Never-Schwarz sector?
Yep.
Yeah. Yes. I think so. Q, B, Q, quadratic. Yeah. The action is given by the B, Q, this G.
G is
integration.
what? Can you say what G is?
G is this.
Okay,
pure gauge field, yeah.
fine. Good. So if it, so the quadratic action I understand. And what about the cubic term? So what is the cubic term?
Cubic term is here. BQ, BB. But quadratic term is not here.
No, cubic is enough for me. Okay.
Cubic is here.
Okay, thank you.
But L2 is, yeah, I think so, yes.
Okay, so it's just a product of V's with Q's and etas and eta bars in some combination.
Yes.
Okay, thank you.
Okay, so Dimitri? You can unmute.
Yes.
Okay.
I can't start my video.
So we can't hear you well.
Okay. So, has my video? Here it is.
So maybe you can try asking question by chat if the connection is not
Can you see
very
me?
good. I can't hear you well.
Can you hear me?
Now it's better a little bit.
Sorry about that. I don't really have internet connection. Is it? Can I ask a question? Is the
Dimitri, sorry, we can't hear you. Maybe he disappeared. Okay. So any other questions? So I have one question. So this dual pure gauge field is pure gauge with respect to what kind of gauge transformation?
This one, dual L infinity, L eta and L eta bar.
So what is the linearized? So what correspond? What is the BRST operator in this the linear operator? The eta and eta bar.
Eta and eta
But
bar. So,
that was the only one, right? Pure gauge.
no, this is the solution of the two compatible equations. Eta, these two.
I see. So it is pure gauge with respect to both of them. Is that what you're saying?
Yes. Yeah.
And it is symmetric.
Yeah, the point is that eta and eta bar has trivial cohomology.
So they can be compatible.
Yes, and then yeah.
Okay, thank you. So we have a little bit more time for questions. No more questions, comments? Okay, if not, let's thank Hiroshi again.
Thank you.
Thank you. So the next speaker is Ashoke Sen from HRR. So are you going to share your screen? Okay, good. So he's going to tell us about Marcel's Ramon sector in superstring field theory. Ashok, please.
Yeah, I'm trying to do full screen. Can you see my screen?
Yes, very good.
Okay, thank you very much. So first of all, I'd like to thank the organizers for organizing the conference and also for inviting me to speak. So let me begin with the kind of questions that we'll be trying to address. Now, the idea of p-brane democracy was introduced by Townsend, in fact, a long time ago. And the basic idea that he proposed is that all p-branes should play equal role in string theory. Now, indeed, this we expect to be true in full non-perturbative formulation of string theory. But because different p-branes have different dependence on string coupling, we don't expect this to be true in perturbation theory. So in perturbation theory, we can make a limited version of this statement. Namely, all d-branes should play equal role. And since a dp brane couples to Ramon p plus 1 form potential, this would translate to the statement that all the Ramon p plus 1 form potentials should play equal role. But this contradicts the conventional wisdom, because the field strengths of the p plus 1 form and the 7 minus p form potentials are dual to each other. And normally, whenever you have a situation like this, only one of the two potentials is included in the field theory action. So today we'll try to address this and see how exactly it works in string field theory. And in the analysis, we'll be using the version of superstring field theory that requires doubling of the number of fields. Now you may think that, okay, because it's a doubling of the number of fields, and that's what explains why you should have both the potential and its dual. Okay, but as you will see, this is not the correct way it works. Now, of these doubling, one set of fields is free and decoupled from the system, and I'll explain how this works. And the other set describes the interacting theory, and that reproduces the usual string amplitude. So this is the usual story in this formulation of superstring field theory. Now, you also know that this theory can be extended to include open strings living on any set of d-branes. And this tells us that somehow all p plus 1 form potentials must be included in this formalism, because in order to be able to couple to d-branes, you need p plus 1 form potential. Field strength is not enough. And the question we'll try to address today is how exactly it happens. It's encoded in this formalism. And here is a reference. Now, there are two papers, one to appear. Now, these papers are actually for studying d-instanton corrections to type 2 string theory on Calabi-Yau manifolds. But in the process of working out the details, we have to work out the construction of the Ramon vortex operators with correct normalization. And for that, we needed basically this framework. So the result that I'm going to describe is contained in the appendices of these papers, okay, and perhaps not stated exactly in the language that I'll be describing, but all the details are there. So let me then begin by describing giving a brief review of classical string field theory. So introduce HMN as the vector space of closed string states of picture number M, N. Okay, so the Mn corresponds to left and right-handed sector, and host number 2, subject to a condition like this. And now we introduce two sets of string fields, okay, which are denoted by psi and phi here. And these two sets of string fields essentially differ in the way the picture number is chosen in the Ramon sector. So you see that this is what you saw. This is the sector you saw in the last talk. This is the additional sector that we add, okay, and that's the doubling that I was talking about. And the action is taken to be of this form. Okay, so here QB is the BRST operator that preserves picture number, and G essentially is the zero mode of the picture changing operator, and it maps H tilde to H. Okay, so G basically acts vertically upwards. QB, of course, takes it out of this Hilbert space because it changes the ghost number. Okay, it is from ghost number 2, it maps to ghost number 3. And this is some interaction term which will not really need to know in details, except that this depends on this set of fields psi and not on the set of fields phi. So this is the action again, okay, what I showed in the last slide, and we can derive the equations of motion from this action, okay, which are given here. So this is the equation of motion for phi, and this is the equation of motion for psi. Okay, you can see that this is simple because phi doesn't appear in the interaction term. And this is what you saw in Olaf's talk yesterday. Okay, that this is what we call the BNs. And this is constructed essentially from variation of this interaction term with respect to psi. Now, it's more useful to combine the two equations and write a third equation. And this is obtained by simply applying G on this, okay, and adding to this and using the fact that G and QB commute. Okay. So this is an equation that involves only psi, okay, and there is no phi. Okay. So you can take this and this as the independent equations. So this is what I have written down here. And now the idea is that once you solve the first equation for psi, you see this depends involves only psi. So this is the interacting field equations that actually gives superstring field theory. Okay. But once you solve this, okay, this is an inhomogeneous equation. That is a source term on the right hand side. Okay. But once we have found one solution to this equation, okay, the only freedom that we have is in adding to phi a solution to this equation of motion. Okay. And these are the free field degrees of freedom. So in other words, once psi has been fixed by solving the interacting equation, the equations of motion for phi just contains free field degrees of freedom. And furthermore, which solution you choose here doesn't really affect the first equation because the first equation is independent of phi. So this is an old story, but I'm just reviewing it, and we'll apply it to the massless sector in a few minutes. So here are the two equations again. Okay, this is the original form of the two equations, which is entirely equivalent. Now it turns out that at generic momentum, okay, a practical way to eliminate the free field degrees of freedom is to simply set psi and g phi to be equal to each other. So you just set psi equal to g phi and write the equation in terms of phi. Okay, so once you set psi equal to g phi, the second equation takes this form. Okay, and then psi is no longer an independent variable, it's determined in terms of phi. But this has to be done at the level of equations of motion. Okay, if you set psi equal to g phi at the level of the action, you don't get this equation. Okay, you get g acting on this, which is quite different. So we'll work with the massless fields in the Ramon-Ramon sector. Okay, and the systematic way to do this is to integrate out all the massive fields. Okay, and as you saw in Olaf's talk, using homotopy transfer, you can do it systematically. Okay. Later, we'll restore the action, interaction terms, and the lost degrees of freedom. Okay, but right now we'll focus on massless fields in the Ramon-Ramon sector and ignore the interaction terms. Okay. So then the second equation also takes a simple form, QB phi equal to 0. And so the idea now is that if we want to study what these equations imply for the massless sector, okay, we simply expand all the fields, okay, namely psi and phi, in components, and then we'll examine how the various potentials and field strengths enter in the expansion. Okay, so that's the goal that we'll be trying to achieve. So we'll be describing the analysis for type 2b, but the analysis for type 2a is almost identical. So it turns out that the expansion of psi is simple in the massless sector. You only have one set of states, which is here. So here, let me just say that the xi eta phi, xi tilde, the xi bar, eta bar, phi bar, these are the bosonized super ghosts. These are the spin fields in the matter sector. And the upper and lower indices indicate that they carry different chiralities. Okay. So here in type 2 theory, the both sectors carry the same chirality. Okay, that's why you see that both indices are down here. Okay. So this is expansion for psi. Okay, the expansion for phi is a little more complicated. It's still a finite set of basis elements, okay, but it has 3 sets of states. Okay. And one simple way to understand these other states is that this is the simple one. Okay. And starting with this, you can just apply the C0 plus beta 0 on this state. That gives you the third state over here. And C0 plus beta 0 bar gives you this state. Okay, so these are the 3 states in the ghost number 2 sector. Okay. So these will now be thought of as space-time fields written in the momentum space. Okay. And let me also add that there is a gauge invariance, okay, in this sector, which takes this form. So A as a matrix gets shifted by the sum of two matrices U and V, where U and V are arbitrary matrices. And under this gauge transformation, B gets shifted to B plus U times P slash. P slash is the usual P mu gamma mu. And D gets shifted to D minus P slash V. Okay, again, P slash is P mu gamma mu. So now the idea is that we'll go back to these two sets of equations that we had, psi equal to G phi and QB phi equal to 0, and see what they translate to in the component notation. So if you look at psi equal to G phi, that gives you an expression for f alpha beta in terms of A, B, and D, because f alpha beta appeared in the expansion of psi, and A, B, and D appeared in the expansion of phi. QB phi equal to 0, okay, is a condition on A, B, and D only. It doesn't involve F, and that's this. Okay, so this you can explicitly work out by knowing the form of Q, okay, and G. And we can easily verify that under this gauge transformation, these equations remain invariant. Okay, so f alpha beta is gauge invariant. So this is invariant under gauge transformation, and this also is invariant under the gauge transformation. So using this gauge transformation, we can actually set A equal to 0. Okay? Because this, you can see that the transformation of A is purely algebraic. Okay? U and V are arbitrary matrices. So you can always adjust U plus V to set A equal to 0. Okay? After that, we still have some residual gauge freedom. Okay? But now U and V are correlated. In fact, V is equal to minus C. Okay? After you have set A equal to 0. Okay? So in this gauge, F takes this form, okay, we just set A equal to 0, and the second equation also simplifies. So the next step is to expand this F, B, and D in terms of tensor fields. Okay. So here is the expansion. Okay, this is the general form of the expansion of F, B, and D. Okay. Because here the both indices are up. Okay, you can easily convince yourself that this involves only odd forms. Okay. And here one index up, one index down means you have to use even forms. However, there is also further constraint. Okay. And this further constraint comes from the chirality constraint on the spinors. Okay. So the way we have chosen our convention is that if you take the product of all the gamma matrices, okay, then the alpha beta component is just identity matrix. Okay. If alpha was up, beta was down, it's opposite chirality, and it will be minus the identity matrix. Okay, that's the convention we have chosen. Okay. So because of this, we can see that we can always insert a product gamma 0 to gamma 9 here, okay, or not here, okay, because this is the upper index over here. Okay. And that converts this index M1 to M2k minus 1, 2k plus 1 to its complement. And that gives some condition that relates F2k plus 1 and F10 minus 2k plus 1. Okay, so these here are the conditions that one gets when you translate this to the component fields. Okay. So each of them satisfies certain constraints under duality. This star here is a Hodge dual. So we are working in flat background space-time. Okay, so here are the two equations again. And now it's easy to decompose this on the tensor components. Okay, so we write F in terms of its expansion in terms of tensors, and so for B and D. And then you can identify individual components by taking trace with the gamma matrices. And this is what we get as the equations for the components, for the tensor fields. Okay, it's just these are exactly equivalent to what we have. Okay. Now these are not very illuminating, but one can just translate this to position space. In position space, these take a nice form in terms of the differential operators. So star here is again the Hodge dual. Okay, D is the usual exterior derivative. Okay. So this is what we get for the expression for F2k plus 1 and the second relation, that is the equation that you get for phi. So now let's collect all the equations. So in the first slide, you see all the duality relations, okay, that B, D, and F satisfies. In the second line, I have given the expression for F2k plus 1 in terms of B and D. And in the third line, I have given the actual equation for B and D. Okay, so this comes from psi equal to G phi, and this comes from QB phi equal to 0. Now, if we use the first equation, then we can see that we can simplify the last these two equations. And the way we simplify it, we basically remove the star, because star bk 2k plus 2 we can replace in terms of b10 minus 2k plus 2. Okay, and similarly for this. Similarly here, we remove the star by using the first line. So if you do that, then the equations take this form. And this is suggestive because now you see that f2k plus 1 is given in terms of only the difference, d minus b, right? There are different ranks, but it's always the difference d minus b. So now we define this new tensor C2k, which is just B2k minus D2k by 2. And then we rewrite these equations in terms of these. Now, let's say that, okay, once you have defined C2k this way, now you see that there is no further constraint, duality constraint on C2k. Because if we take the dual of C2k, that goes to B10 minus 2k plus D10 minus 2. Because there is a change of sign, here is a k plus 1 and here is k. So this minus sign will get converted to plus sign. So that's a different set of objects altogether. So once you have written it in terms of C2k, there is no further constraints. So C2ks are all independent fields. So now we can rewrite this equation in this form, which looks simple. So f2k plus 1 is given by this sum, and C satisfies an equation of this form. Okay, again, this came from psi equal to QB phi. This came from the equation of motion for phi. Okay, QB phi equal to 0. So here is here are the two equations. Okay, so these are the final equations at the level of free fields. Okay. And now we can interpret C2k's for different k as the Raman potential, and f2k plus 1 as a field strength. Okay. So you see indeed that we have all the potentials. Okay. And the fact that we have all the potential is not directly related to the doubling that I talked about, because the doubling basically is the fact that we have both F and C. Okay. In fact, if you look at the level of the fundamental field content, okay, we have tripling. Okay. Because we have C2k, we have C2k for all k. Okay, so that already gives the doubling of the degrees of freedom. Okay. And on top of that, we have F2k plus 1. Okay, so the actual field theory action will contain all three. Okay. But of course, at the end, you get back the same superstring field theory physics, superstring theory physics, after you use your equations of motion and eliminate the free fields. So the role of this equation, okay, is to set dC2k and dC8 minus 2k to be dual to each other. Okay, that's what is telling us that these, even though at the level of the potential these are independent fields, okay, equation of motion relates their field strengths to each other. Okay. And with the help of the second equation, the first equation can be written either in terms of C2k or in terms of C8 minus 2k. So you can write this as the f2k plus 1 as the dual of dc8 minus 2k, or just as dc. So this is as much as I'll say about the equation of motion at the level of the free fields. And now we are going to examine how string field theory action leads to these equations. Okay. So we'll be starting first at the level of the free string field theory action, and then we'll generalize, we'll include the interaction terms. So here are the two equations again. Okay. And now you can ask, what is the string field theory action? Okay, that is responsible for these two equations. Okay. And we'll write down the string field theory action in the A equal to 0 gauge, because as I said, this is just an algebraic, the gauge transformation acts algebraically on A, right? So you can always use it to set A equal to 0. Okay, you don't really lose anything. You have all the equations of motion intact.
You have 5 minutes.
Okay, thank you. Okay. So in the A equal to 0 gauge, okay, this is the string field theory action. Now, from here, it immediately follows that if you look at the equation for f2k plus 1, then you immediately get the second equation, this one, right? Because that just sets this equal to 0. Equation of motion for C, 8 minus 2k. So here, it's a little more complicated to see, but actually there are a lot of simplifications. So let me say how we can simplify. So first of all, okay, because the sum runs over k equal to 0 to 4, you can easily convince yourself that under k goes to 4 minus k, okay, these two terms get exchanged. Okay. So you can just drop this. Once you have used the sum from k equal to 0 to 4, you can just drop this because it essentially repeats it twice. Once you drop this, then the star with star gives you just identity up to a sign. Okay, so you have dc 8 minus 2k. Okay. And that allows you to just drop this term because this is a total derivative, right? dc to k wedge dc 8 minus 2k. So that's a total derivative. You can drop this. And then it's easy to work out the c8 minus 2k equation. Here it is. Okay. This is just added by hand because you see d of d is 0 anyway. Okay, so this is not significant. Okay. But I have just written it this way to make sure that this is self-dual. Okay. So this is almost the first equation, except that we have possible solutions of plane waves that we can add. Okay. This is not quite this, right? Because you can add to any solution of this, okay, the solution of d of something equal to 0, d of this self-dual field strength equal to 0. Okay. And this, of course, is not surprising because remember that the actual equation that we expect from string field theory is this, okay, and not this, right? This is what gave rise to this equation, okay? Whereas the actual string field theory equation is this. Okay, so now let me introduce interactions. Okay, so here is the interaction term, okay, besides the free action. So the important point here is that the interaction term depends only on F because psi contains F but not C. So because of this, the equation of motion for C remains unchanged. So that's here. And the equation of motion for F gets correction, okay, which is here. Okay. So let's now try to analyze these two equations and see what we get. Okay. So here are the two equations. Now, using the second equation, the first equation can be simplified. Okay. In fact, star C can be, dc can be eliminated, and then the d of d is 0. Right? So basically, the first equation just gives you something that involves only F. Okay. And this is the analog of the condition that you could rewrite the equation for string field theory in terms of psi only, right? Remember that F appeared in psi. Okay. So this is the interacting field theory, interacting equation for the Ramon-Ramon fields. Okay, this contains all the dynamics of Ramon-Ramon fields in string theory. Okay. Once you have solution to this, okay, the second equation can be solved. Okay. And the only freedom that you have in solving this is to add solutions to the free field equation of motion. And that's just a set of free fields which completely decouple from the system because this doesn't react back on the F equation of motion, which is here. Okay. So that's the way the Ramon-Ramon sector works in string theory. So let me now turn to the conclusion. So what we have seen is that the massless Ramon-Ramon sector in type 2B superstring field theory contains a set of field strengths that satisfy self-duality constraint, okay, and then a set of Ramon-Ramon potentials without any self-duality constraint. Okay. This is determined by a set of interacting field equations, okay, which depend on the other fields but not on C. Okay, and this indeed is the actual dynamical field equations in superstring theory. And once this is given, this is fixed up to addition of solutions to free field equations of motion. And as I already said, that these solutions are plane waves, and addition of these do not affect equations of motion of any other field. So now let me just add one more point here, that from this it would seem that the role of C is purely technical. Okay, that at the end just went away. Okay. And indeed this is true if you are considering pure closed superstring field theory. Okay. But once you couple it to D branes, C's play a crucial role because you cannot couple closed string fields to D branes with field strengths only. Okay, you need the potential. Okay. So indeed, in the presence of D branes, okay, C's have another term, which is a linear term in C. Okay. It still remains a free field, okay, but we have to add the linear term, and the only way to couple D branes to the rest of the system is to have the C's. Without the C's, you couldn't couple D branes to the rest of the system. Okay, so they do play an important role when you include D branes. So with that, I'll stop. Thank you.
Thank you for the very clear talk. Any questions or comments?
Can you hear me?
Yes, please.
Yes.
Are C fields annihilated by supersymmetries?
Pardon, sorry, I didn't hear you.
Sorry.
Ashok, he asked if the C fields are annihilated by supersymmetries.
Yes.
C fields, okay, they have linearized supersymmetry, but indeed otherwise, okay, let me put it this way. The transformation of the C fields is, it's not annihilated by supersymmetry, but it depends only on the F. Okay. So, I mean, forget about supersymmetry, even under general coordinate transformation, right? The C fields don't transform in the usual way. Okay. Usually, you will say under general coordinate transformation, the C will have a term involving derivative of C. Okay. But the way this formulation is set up is that the transformation of C under anything depends only on the F's and not on the C's, including general coordinate transformation. So the C's are not singlet under supersymmetry, but their transformation involves F.
Thank you. Very interesting. So it's not true that equations of motion, that field equations of supergravity are unique for this, are uniquely fixed by supersymmetry, because
That they are unique.
I thought that equations of supergravity are uniquely fixed by requirement of supersymmetry. That was the conventional wisdom, but here you have some additional components which satisfy wave equations. But
yeah, I think that's not quite true, because this certainly we have checked that this gives exactly the same theory as supergravity, okay, except that you have these extra free fields. Okay, and there is a complicated field definition that takes you from here to supergravity.
Sorry, there is field redefinition which takes you to supergravity, or?
Pardon?
Or these are additional components which are not present in supergravity.
The additional component C. Yeah. So what happens is that the supersymmetry as well as all symmetries are realized somewhat in a non-standard fashion. Okay. Because if you look at the string field theory gauge transformation, okay, the transformation of C, it can contain a linear term. Okay. But then everything non-linear involves only F. But nevertheless, this theory that we get is exactly equivalent to supergravity. That one can check.
Okay, thank you.
Any other questions?
Yeah, one
Comment?
question, Ashok. By the time you couple the D branes to this theory and the C fields, how do the Fs know about the D branes, or do they know about the D branes?
Yeah, well, Fs do not directly know, but what happens is that there's a linear term in C.
Yes.
So you have to feed it back to the F equation, right? So ultimately, the way we got the F equation is by combining with the C equation.
Okay.
So if there's a linear term here for the C, that translates to the F equation. You can eliminate this. Okay. So this is a C equation, right?
Yes.
So what happens is that now, because of the coupling of the C's, there's a linear term on the other right-hand side. This equation remains unchanged. Now you add this to this to eliminate the C, but the F equation now gets a term on the right-hand side.
Nice.
So the D branes do appear as source of the F equation.
Okay.
But in the action, you cannot couple it without the C.
Okay.
Which is, I mean, something that you are familiar with even in electromagnetism, right? That you cannot use F to couple to charge fields, right? In the action, you need the MUs.
Yeah.
So this is basically the analog of that statement.
Good.
So a linear term on the right hand side of this equation essentially translates to that after you combine with this and write it in this form, okay, in this form, F equation gets something on the right hand side.
I have a question to Ashok also.
Yes.
Yeah. So this equation on the top of the slide. So do I interpret it correctly that you always have this free decoupled C field, which the plane waves are always solutions, even if the F equations are not satisfied?
Yes, indeed. I think, well, I don't know exactly what one means by this, because the C equation to begin with had this structure, right? So the freedom of in the C is addition of the free field degrees of freedom. But I think the ability to solve this will require the F equation to be satisfied.
Well, otherwise it would be inhomogeneous, just that's probably, no.
Otherwise, I think there will be inconsistency, that you will not be able to solve this equation unless the F equation has been satisfied. Because, yeah, I mean, if we go back to the original set of variables, right, I think it's easiest to see in the string field theory language. Yeah, so these are the two equations that we get. Okay? Mm-hmm. And you have for arbitrary psi, you may not be able to solve this, right? Because you need this one to be BRST exact, right? So, and for that, you need the F equation to be satisfied.
Oh, I see. Mm-hmm. So it forces psi to zero. I mean, it forces psi onto a solution in some sense.
Exactly. Yeah, yeah. So I think it's easy to visualize in this, that in order to be able to solve this, you have to first make sure that this has a solution.
I see.
So I think we should move on to the next talk. So thank you very much for the very nice talk, Ashok.
Thank you very much.
The next speaker is Shi-In from Harvard. So could you share your screen?
Yes. Can you hear me?
Yes.
Yeah. Okay. Should I start?
Okay, so he's going to tell us about the 4 applications of SFT. Please.
Thank you very much for the invitation to speak. As someone who kind of came outside of the string field theory community and has grown to appreciate the subject, I would like to take the opportunity to discuss not so much of a report on results, but to focus on questions. And with the hope of drawing the attention of the experts to these questions, and in particular, I will talk about 4 areas of physical questions in string theory, which I think the formalism and technology of string field theory can be readily applied and hopefully make progress in the near future. So the first thing I want to discuss is Raman-Roman flux in superstring theory. So the standard paradigm for the perturbative superstring theory is based on a Hiroshi CFT with the BRT symmetry. Now, for general weakly coupled string theory, this Hiroshi CFT, in the sense of a local conformal field theory, may or may not exist. So, for example, consider type 2 string theory in Raman-Roman flux background. Now, naively, one might, following the story of NS-NS deformation, one might think that Raman-Roman background deformation should be represented by deforming the Hiroshi action by the Raman-Roman vertex operator, which is usually written in a -1/2 picture. But if you want to actually deform the action in a way that makes sense, you have to kind of convert the picture to the correct picture number, and you might work with an expansion like this, as was proposed by Berenstein and Lee in '99. While this may be morally correct, it's really only expected to be correct up to BRT transformation, and this form of the Raman-Roman deformation, as it was written, which it's not completely correct due to subtleties having to do with regularization, would in any case seem to be non-local from the worldsheet point of view. It's sometimes local up to BRT transformations. And I want to also point out that the Raman flux, this is not unrelated, that the Raman flux is generally needed in the known constructions of holographic confining string background. Now, so, and you know, there's a big question of, for example, we would like to know what is the worldsheet theory of the flux string in 4D pure Yang-Mills at large n. It's a weak coupled string theory, and we'd like to know whether there's a worldsheet CFT. It may or may not exist, and I think this may not be unrelated. So now, in the NSR formalism to superstring perturbation theory, there is a first principle approach to Raman flux. This is based on the NSR closed superstring field theory. As the equation motion, as Ashoke has already written, takes this general form. And you can think of the Raman flux background simply as a solution to the equation of motion. And expand it, we can try to find such solution perturbatively in the Raman flux deformation parameter, which I call mu here. So this Raman background will be represented by solution psi 0 of the string field equation of this form. And then we can perturb around the solution. So psi 0 can be determined perturbatively, given that the string field action is determined perturbatively. And then we can expand around this and try to study the spectrum of linearized fluctuations to begin with. And that will teach us about, for example, the superstring spectrum in the Raman flux background, perturbatively in R flux. Now, with Scott Collier and Minjae Cho, we did this for ADS 3 times S3 background to the leading non-trivial order in the Raman flux back in 2018. But the higher order is yet to be studied. And I think this a harder problem, but I think it's within the same framework that can be attacked, is a first principle calculation of the string spectrum perturbing 1 over R in ADS 5 times S5. Okay, so the second thing I want to discuss is the instantons. Now, you know, we know that the worldsheet formalism of string theory goes beyond perturbation theory. It can also capture e to the minus 1 over GS effects, which was already recognized by Joe Polchinski even before D-branes were understood. And this worldsheet instantons are D-branes localized in space and time. And they contribute to closed string scattering through worldsheets with boundaries, like this picture on the right-hand side here. In a standard on-shell approach to this calculation, one encounters open string divergences, among other issues, whose regularization requires open plus closed string field theory. As was explained in glory detail by Ashoke Sen in the last couple of years. I want to focus on one example here, which is 2-to-2 graviton scattering type 2B superstring theory. This is perhaps the most basic non-trivial scattering amplitude at a full non-perturbative level. So the amplitude is well known to be constrained by supersymmetry to be the supergravity amplitude multiplied by a scalar function, a single function of the Mandelstam variables and on top bar, which are the moduli for the type 2B vacua. Now, we can try to understand this. This amplitude is a very complicated object. Its function is a very complicated function. We're going to try to understand it both from the point of view of a low energy expansion and the string coupling expansion. From the point of view of low energy expansion, it has some supergravity tree contribution. It has R, so-called R to the 4th term. There's some loop contribution, and you know and there's higher derivative terms and so on and so forth. There are analytic terms as well as non-analytic terms. Some which are known, like R to the 4th, D4 R to the 4th, D6 R to the 4th. Some others are not known, most of which are not known. There's also a string coupling expansion, which schematically takes the following form. There's a closed string loop expansion in 1 over tau 2, which is a string coupling. And then on top of that, we expect to have an instanton expansion. So for example, you have a 1D instanton contribution goes like e to the 2 pi I tau. You have one anti-instanton goes like e to the minus 2 pi I tau bar. And for each instanton order, there's going to be an open string loop expansion, which is the expansion in powers of 1 over tau 2 rather than 1 over tau 2 squared. So now there's some caveats to this kind of summation formula, because to write the sum really would only make sense if you know how to Borel resum or how to resum somehow the perturbative series. But you know, some of the contributions are unambiguous. For example, the one instant contribution is unambiguous compared to the perturbative one, because the perturbative contribution only depends on tau 2, whereas instant corrections also depends on tau 1. In any case, so one can study, for example, the one instant contribution at the leading open string loop order, which will be given by these 4 disk diagrams with some integration over the bosonic and fermionic moduli space. This is well understood, and it only contributes to the R to the 4th coefficient. You can go to the next order, which is the 1 instanton contribution, but at the next order in the open string loop expansion, which involve these diagrams. So now things become interesting because they involve open string divergence. The naive on-shell calculation would run into potential open string divergences. In fact, the naive on-shell calculation will give you an answer that looks like this, where the size are digamma functions. So you can use that to produce a all order momentum expansion for the 1 distant contribution at this open string 1 loop order. The problem with on-shell calculation is that it is ambiguous at the level of this constant A I wrote here, just one constant, in fact, one can argue, and it gets it wrong. In fact, with Nathan, Agman, Bruno, and Minjae, and Victor, we did this calculation a little while ago, and we got the constant wrong from the explicit on-shell calculation. But it's really just ill-defined in the on-shell approach, and this requires string field theory to fix. Just to say exactly what is the meaning of that, this coefficient A, which you cannot quite get right from the on-shell calculation, is the coefficient of e to 2 by tau 2 to the -1, R to the 4th coefficient. Now, so for a long time, we've been trying to directly calculate this A using string field theory and hope to land on the right answer. We still haven't finished that calculation. However, there's a shortcut that allows us to fix A and argue that it's in fact determined to be the correct answer in the string field theory framework as following. So in fact, first of all, this constant A can be fixed by supersymmetry. So this is because supersymmetry actually constrains the R to the 4th coefficient to obey a differential equation on the moduli space of type 2B vacuum. This argument based on supersymmetry is not totally trivial. It relies on supersymmetry order identity constraining the 6-point amplitudes and relating 6-point to 4-point. In any case, as I said, the naive on-shell calculation will get the wrong answer for A. And that will be incompatible with space-time supersymmetry. In the string field theory approach, the supersymmetry is ensured by the BV formalism. Even though the BV gauge condition, as Ashoke has explained to us in recent work, one needs to, first of all, adopt a gauge condition, the BV gauge condition that's different from single gauge condition. I will call it the same gauge. And the gauge condition is not manifestly supersymmetry invariant. So the individual string field diagram is not going to give manifest supersymmetry answer, but the physical observables in this formalism are guaranteed to be SUSY invariant due to the gauge independence of the BV formalism. So the supersymmetry, once you know the calculation is well defined, all the pieces are finite, it must be consistent with supersymmetry, and so the string field theory must be the answer for A that is determined by supersymmetry. Let me just briefly mention that there are some interesting open question about uncharged d-instantons. For example, a pair of d-instant and anti-d-instanton. In the on-shell approach, you will encounter a singularity in the moduli space of d-instantons where the separation of d-instanton is such that there's open string tachyon that goes on-shell. One could wonder whether the integration of the instant moduli space is well defined. In the sequence 1 string theory, in work with Bruno and Victor, we came up with a contour prescription to get around this issue. But in a type 2B superstring theory, this is less clear. And it's perhaps more than just a technical problem because it's also related to the question of how to sum up the closed string perturbative series, because in general, the uncharged instant contributions is not clear a priori how to distinguish it from contribution from the summation of the perturbative series. Okay, so the next thing I want to briefly discuss is string theory and time-dependent background, which one often makes complaint about. So the worldsheet formalism based on a conformal field theory is simply deficient to describe a general time-dependent background string theory for the following reason. So usually we define the worldsheet CFT in target space in the nonlinear sigma model language through a wick rotation procedure. That is, we want to replace the time x0 field by Euclidean time. Once you do the wick rotation, you might hope to get a unitary matter CFT. This would make sense if the target space time is static, so that the G mu of x is independent of x. So after this wick rotation, you have a real and positive definite action. Now, in this procedure, after you do the wick rotation to Euclidean signature of a target space, it becomes a unitary CFT in the matter sector. We can construct a standard CFT Hilbert space with operators like e to the ikx. We compute correlators of these operators, and then we continue these correlators back to Lorentzian signature. Now, I should say that even in the case of static spacetime, this is not totally trivial. For example, in the case of ADS3, we really have to understand the Euclidean version, which is H3 plus model, and then continuation back to Lorentzian signature is non-trivial, but understood in that case. This doesn't work for generic time-dependent background, and perhaps for good reasons, because in time-dependent background, we expect the choice of vacuum states in space-time, and it's a priori not clear how to define the notion of asymptotic states and S-matrix elements. And it's not clear what are the right set of physical observables. Now, I think string field theory is a suitable language to address these issues. In fact, there will be a talk that I look forward to soon today on this. In string field theory, once again, we can expand around the time-dependent solution to a string field equation. The solution can be found perturbatively in a situation in physical problems of interest. And we can do perturbation theory in the fluctuations around the time-dependent background. And I think this is kind of a nice thing to do to address issues concerning particularly the dynamics of tachyon, say closed string tachyon. If you try to do perturbation theory around, in a closed string theory with closed string tachyon, that's not supposed to make sense. And the basic physical reason for this is just that the tachyon sitting at the top of the potential, quote unquote, does not approximate any quantum state. There's no such quantum state that corresponds to, because it's gonna roll over in any quantum setting. But a rolling tachyon is expected to be physically a good approximation of a quantum state in some suitable limit. And one would expect to have a sensible time-dependent perturbation theory around the rolling tachyon background. I'll have a little more to say about this in the context of open-closed duality. So finally, let me come to the open-closed duality. I want to contrast the open-closed duality that I'm referring to here to, let's say, ADS-CFT correspondence, even though one often loosely refer to ADS-CFT as an example of open-closed duality. Let me recall the logic of ADS-CFT from the decoupling limit. So we got a D-brane, same type 2B string theory, and we think it's the same as a black brane solution, which is a closed string background. And we take the decoupling limit or near horizon limit of the black brane, and we find ADS throughout. Now, this chain of reasoning really has two steps, which I want to distinguish from one another. The first step is what I would refer to as open-closed duality. That's the equivalence between the D-brane and the black brane. The second step is the decoupling limit. This requires a manifestly covariant patch-by-patch description in order to go from the asymptotic flat black brane solution to the horizon. And while this is well described in the low energy effective theory, such as GR, which is covariant, I think the current formulation of string field theory doesn't allow you to do that. So I don't know how to do this in string field theory, but the first part, this open-closed duality, I think can be understood from open plus closed string field theory. In fact, now I think we have a nice technology for dealing with this, thanks to the work of Minjae Cho following the earlier work of Costello and Zwiebach on these hyperbolic vertices. So one can define these hyperbolic string vertices for open plus closed string field theory. In Minjae's formulation is labeled by a pair of parameters called L open and L closed. So roughly speaking, if you put hyperbolic metric on string worldsheet, then the open string stops on the open string part of the boundary of the string vertex is going to be constrained to be length L open, and the closed string part will have a length L closed. Heuristically, well, it's more or less clear that in the limit, when you send L open to 0, you are integrating out most of the open string modes, and you end up with a mostly closed string field theory. In the other limit, when you send L close to 0, you integrate out most closed string modes, and you end up with the most open string field theory. And Minjae showed that the allowed admissible choices of L open versus L closed is in this this bounded region here. Well, not bounded region, in this region here. So there's some maximum value for L closed, but there isn't a maximum value for L open. Now, you can move around this allowed region by which amounts to different choice of string vertices that correspond to different string field actions related by field redefinition. So there's a string field, open plus closed string field redefinition that allows you to move from one point to another point in this allowed space of parameters. On the blue line here, on the left side, where you take L open to 0, here we expect to get a closed string field theory with a D-brain source. On the other hand, in this red part of the diagram, where the L closed goes to 0, you expect to get a purely open string description. In fact, when L open goes to infinity, and simultaneously L closed goes to 0, you recover Witten's cubic string field theory. Minjae did not say this in his paper, but I checked with him yesterday that he agrees with the statement. Now, a clean setup for this question, really, so we need to focus on theories that actually make sense at a quantum. We would like to focus on theory that actually makes sense at quantum level. And a clean setup for this is the rolling open string tachyon on the ZZ brane in C=1 string theory. There's a matrix model picture, a dual matrix model picture that helps illustrating what is going on. You have a matrix model which admits a free fermion description. There's a Fermi C, which is this gray stuff over here. And then the ZZ brane is a single fermion that comes in and bounces back from the potential. If the ZZ brane sits on the top of the potential, if the fermion sits on top of the potential, that's like ZZ brane where the tachyon is just barely turned on. And you can contrast the left-hand side of the matrix model description to a cartoon for some kind of tachyon potential. This is not precise because the tachyon dynamics is not really described by two derivative theory, but nonetheless, there's a cartoon. The shape of the top of the potential together with the top of the Fermi C is kind of like what you expect of the tachyon potential to look like. Now, if you go to the right side, you go to the closed string vacuum. Condense on the right side, you go to the closed string vacuum. Going to the left side, you go somewhere else. First point is that the classical open string field theory on the ZZ brane is identical to Witten's cubic open string field theory, with the exception that you truncate to the vacuum module of the C=25 matter CFT. But things like Schnabel's solution of the tachyon condensation applies directly to this setting. The interesting question is whether one can make a sense of the quantum open string field theory or open plus closed string field theory. And I think to do this, one needs to expand around the rolling open string tachyon solution, because otherwise, the open string tachyon is such that the naive loop expansion doesn't make sense. But I think if you expand around rolling open string tachyon solution, then the time-dependent perturbation theory based on the open string field theory should make sense. Perhaps, the expectation is that the rolling open string tachyon admits an open string description as well as a dual closed string description in terms of the closed string radiation, and that should be related by a string field redefinition. And basically, what you need to do is to go from sort of this Witten's cubic description all the way on the right part of this diagram, all the way to the left part, and then go from open to closed description.
You have 5 more minutes.
Okay, my time is up, and so I will just.
No, you have 5 more minutes.
Oh, okay. Well, I will conclude anyway. Leaves more time for discussions and questions. In conclusion, I think the formalism of string field theory can overcome a number of deficiencies of the Ansha approach. In all of the previous examples, each example is a situation where the Ansha formalism of string field theory simply cannot address the questions of interest. I think string field theory can. I think the technology is available, they're at least working perturbatively, and there's much work for you guys to do. And I hope this is really an invitation for you guys to think about these problems. Thank you.
Thank you for the very nice talk, for many interesting materials. So if you have questions, please raise your hand virtually. Let's see. Nathan?
Hi, thanks for the nice talk. So I have maybe a philosophical question. So there's a problem with doing I guess you want to call it non-perturbative or finite Ramon-Ramon background using RNS. Do you view this as a problem of string theory or as a problem of the RNS formalism?
So you're complaining that the working perturbative in R flux may not be enough.
Well, it's not enough, right? I mean, it's perturbative.
It's perturbative, but there's a question of, okay, so but I mean, philosophically, it's important to address the question of whether the perturbative expansion converges or not.
No, I'm just asking, suppose you want to find ADS5 times S5 with a finite radius. We can't do it using RNS. Is that a problem, or is it something that, I mean, is it a problem?
Do we really know that? Do we really know that we cannot do it? Because you can wonder if you, in principle, as a matter of principle, if you can sum up the perturbative series, there's a question of whether you can make sense of the summation. But I'd like to distinguish from the situation of, let's say, string perturbation theory in G string, where we don't think that at least any kind of simple summation prescription can produce the exact answer. But in the case of our background, I'm not so sure. I think in many examples, I would actually expect the perturbation theory to be to converge to the expected answer at finite deformation parameter.
Okay, so you don't view it as a problem of string theory. You just view it as it's just we don't have a non-perturbative definition, but okay, we don't need one.
I'm not making such a strong statement. That I think there are some examples where the perturbation theory, in principle, can give the full answer. I'm not saying that that's always the case. Certainly, in a situation where there's a topology difference between the background without Ramon flux and the background with our flux, it's I think in that case it's not so clear that you can really get all the finite R background. But I think one should not dismiss perturbation theory just because it's an expansion, because sometimes the expansion do converge.
Sure. Okay, thanks.
So please raise your hands if you have questions or comments. So I have one question. So you mentioned the setup with a ZZ brain.
Yeah.
Could you show me the slide? So what is the so in the open string description correspond to the flat background with ZZ brain? I mean, may not be flat, but with a ZZ brain. What is the other side?
Oh, you're asking the other side, I mean the left-hand side of this tachyon field?
You're talking about the open closed duality, right? So what is the dual description?
Oh, the dual description. Well, it will be some closing radiation that we don't really know about. I mean, in the early 2000s, I mean, they are.
No, I'm before introducing rolling tachyons. So just background with before introducing the rolling tachyons. So what is that's a ZZ brains, and what is the dual geometry? What do you expect?
Geometry. There's you want to take some kind of decoupling limit. I don't think that question. I don't think there's a well-defined answer to this question, because precisely because I think the ZZ brain without turning on the tachyon is unstable. Does not correspond to well-defined quantum state. So I don't think that makes sense as a quantum state, and I don't think there's necessarily a good answer to the question of what is this dual.
But then you're saying that if you...
Yeah, I would say the rolling tachyon is a natural thing to consider. Now, you see, the rolling tachyon, it can have energy close to the top of the potential. So it will take infinite amount of time. It will spend infinite time near the top of the potential, but then it's going to decay away. But if you take the energy to be close to the Fermi surface, then it's almost indistinguishable from closing background. So we have a one-parameter family of solutions that interpolate between something that spends a lot of time looking like a ZZ brain and before it decays away, versus something that is almost in the closing vacuum. But I think this is the thing that one should be studying, rather than the quote-unquote ZZ brain without the rolling tachyon. I think one should always study ZZ brain with the rolling tachyon rather than without the rolling tachyon, in other words.
Okay, thank you. Thank you for the explanation. So, Rajesh?
Hello. Hi, Sheet. A nice talk. So I wanted to have your thoughts on in this open-closed string duality, one context where you don't really have to take the second step that you mentioned of decoupling in your two-step case. One case where you don't have to do that is the case where you have topological open strings with giving you Chern-Simons theory being dual to a topological closed string. So there, in some sense, the Witten's open cubic open string field theory is the Chern-Simons theory, and you don't really need to take any separate decoupling. So I was wondering whether that could be a good test case in the context of what you showed of this field redefinition in moving in the space, connecting the Witten open string field theory to the closed string field theory, where you know that the closed string field theory is some kind of the topological A model on the conifold, the resolved conifold. So is that something you think that case might be a tractable one for applying this formula?
That's a very interesting suggestion. I haven't really thought about it, but I think that's a very interesting suggestion. Perhaps. I mean, you know, in fact, I'm happy that I gave this talk because, you know, these are precisely the kind of questions I would want to think about. Thank you.
So in particular, if I can try to understand that picture that you had of interpolating between this one. So when you say there's a string field redefinition, is that redefinition explicitly known as you move at least infinitesimally?
So this deformation has, it's more or less, I would say explicitly, depending on what you mean by explicit, at level of infinitesimal deformations. So if you move by infinitesimal step in this space of parameters, then there's the general formalism that you know, has been explained, I guess, maybe first by Barton. I'm not entirely sure of the history of this, because you know we change the string verses, but they all obey this master equation. And generally, if you deform the string verses a little bit, let's say by changing the domain of integration in the moduli space, there's a general prescription for figuring out the corresponding infinitesimal string field definition. So we know infinitesimally how to move, and you can compose these together. So in principle, that is known. In practice, it's going to be something perhaps very complicated. So there's some technical challenges to make this explicit calculation.
Yeah, and perhaps starting with L0 equal to infinity is perhaps a sort of singular point to deform away from, or is it like at finite distance, so to say, or?
That's a good question. But you know, even if you are just a large L naught, it's finite L naught, L open, but at the you know close to zero, that's still a limit of open string, purely open string field theory, just not Witten's one, because instead of just having cubic vertex, you have quartic and all the higher. But I don't really see a obvious obstacle to connecting these.
Yeah, no, I had in mind because
I mean, there was this long-standing idea that if you just a level of the geometry of Riemann surfaces with boundaries, if you take the loops formed by Witten's vertex, you cover the entire modular space. So you might think that the perturbation theory based on the open string field theory will cover everything, except there's a technical problem that there's the open string tachyon, and in the superstring case, there's additional there's no open string tachyon, but there's subtleties involving the PCO. So and spurious singularities. So, but if you do this, try to make sense of the perturbation theory around the rolling tachyon background, I think potentially it will make sense. You can potentially because at least physically, I don't expect to have the same problem as expanding around the where the tachyon field is not turned on, which is why I was suggesting, thinking about this question specifically for the rolling tachyon background.
Okay, thanks.
Okay, let's thank again. Let's thank Shi again for the very nice talk. So the next session starts as scheduled. Harold.
So we start again at 9:45, so in 8 minutes.
Okay.
So thanks to all the speakers of this morning, and thanks to Yuji for chairing the session.
Okay, so we start with this other session of today's meeting. So the first speaker of this session is Minjae Cho from Harvard, and he's going to tell us about type 2B, the instanton amplitudes in of zero modes. So.
Thank you very much. I wish to thank the organizers for this wonderful workshop and also for giving me the opportunity to give a talk here. So we've heard lots of great talks today. I'm going to tell you about something that's more graduate student minded. So there's a subtitle which says that what a curious graduate student might ask. So typically when we first take string theory class, we learn how to compute Veneziano amplitude, and then we learn about D-branes. And then one curious graduate student might say, oh, what if we compute something like that in the instanton? And then he or she will run into a whole bunch of confusions. So that's what I'm going to tell you about today. And this is a work with computation that I've done with Nathan Ackerman. And the bosonic story of this computation was already discussed by Ashoke Sen in this beautiful paper. And Nathan and I were motivated while we were computing the closed string amplitude in the instanton background for type 2B, the work that she mentioned. So this computation involves lots of string field theory computations if you want to fix that unambiguous constant that she mentioned. And before attempting that, we actually wanted to make sure that we understand some of the basic machineries of this string field theoretic computation. And that turns out to be this computation. So I guess in this community, this diagram basically clarifies or summarizes the computation that I wish to present. So we have a disk with type 2B instanton boundary condition. And we have 4 insertions of the open strings, and they are the translation zero mode. So this phi mu is the string field for the translation zero mode, and this is a vertex operator. And because these are in picture -1, we have to put 2 PCOs in, okay? And the question is whether this is equal to 0, because these are moduli modes. So when we think of the effective potential for these modes, it should be 0, where by effective, I mean when we integrate out the massive open string modes. But it turns out that there's a whole bunch of ambiguities in there in this computation. And this question mark involves things like gauge choice or the Lagrange submanifold, and also partial Zeit term, and possibly vertical integration, which is also part of this partial Zeit term. So let's see. So type 2B instanton background for the open string modes, there are these interesting ones. These are the 10 bosonic moduli and 16 fermionic moduli for the broken symmetries realized by this instanton background. And explicit form of them can be written like this. And this epsilon is a string field for these fermions. And the expectation again is that the effective potential for these zero modes should be 0 because they're the moduli. And we can go and check whether that is true, just, like 3 point, 4 point, and da, da, da. So at 3 point, you can compute things like, phi cubed or phi times epsilon squared. And these are trivially 0. You can easily check them. At the level of 4 point, you can also check epsilon fourth or phi squared, epsilon squared, and they're also almost trivially 0. The first non-trivial thing that happens is actually this phi to the fourth. And basically, of course, at a higher point, like higher annuli, you'll run into a whole bunch of different complications. So let's see what I mean by that. So here's a naive computation. We have 4 insertions of this vertex operator for the translation 0 mode, and we have 2 insertions of the PCO. So one of the operator is integrated, and we are integrating it over the disk, the boundary of the disk. And this is the computation of, result of the computation of the correlation function. And these f's are some function purely of the location of the PCO. And as you can see here, there's some divergence when x nears 0, 1, and infinity. It comes from some colliding singularity. And typically in D-brane case, what we would have done is that, in D-brane case, if you are strictly, confining to the 0 momentum case, then you're running into the same divergence. But then you can say, okay, let me consider generating momenta. And after computing everything, you can send momenta to 0, and then you correctly get 0. So there is some analytic continuation involved there. But actually, for the instanton case, which has 0-dimensional word volume, there's no continuous momenta. You can analytically continue. So it seems like there's some genuine divergence. Actually, there's one cheating you can do, which is to put one PCO at the integrated vertex operator and the other PCO in the bulk, and then it actually correctly gives you 0. And this somewhat natural from the perspective of conformal perturbation theory, where you deform the background using the exact marginal deformation. But actually, this exact marginal deformation involving PCO is kind of ambiguous. At higher points, such tricks will actually run into further ambiguities. And the more correct way to talk about it is actually as a solution to the stream field equations of motions. But here, I'm just going to compute this using the strict stream field theoretic way. And let's see if we get 0 or not. So the first ingredient that stream field theory gives in extra to the unshelled computation is something called ghost zero modes. So this was discussed by Ashoke in his paper. And in the, these are the states carrying weight 0, and then they have only purely ghost excitations, and these are all of them. And typically a single gauge, which sets, B0 ghost acting on them to be 0, you basically get rid of this first term and the last term, and you're left with the second and third term. But the thing is that they're weight 0, and if they're in single gauge, their propagator, their kinetic term in the action evaluates exactly to 0. So they actually lead to singular propagator, and perturbation theory thus is ill-defined. So instead, what Ashoke said was that, okay, these are familiar fields and anti-fields in the stream field theory language. So let's just set the anti-fields to 0 and see what happens. So this psi upper 1 gets some finite propagator, which is good. The psi upper 2 still gets 0 propagator, but actually decouples from the rest due to the ghost number conservation. So we can expect that, okay, now the perturbation theory in this case is well defined. So this psi upper 1 is what I'm going to call ghost zero mode from now on. This ghost zero mode has a finite propagator because it looks like this. And we know what the stream field action looks like. So we are just doing Feynman rules now. So say we have some cubic vertex like this, where they involve this ghost zero mode, then diagram like this must be added by hand. Okay, we take vertex squared and multiply by the propagator. And this is 4-point Feynman diagram. So in the operator language, this is how it looks like. You might say that, oh, there's this zygote, and it typically contracts only with the eta ghost. So it seems a bit non-standard, but don't worry, this PCO actually includes eta-dependent term. Sometimes people actually do not quite appreciate that there are these extra terms in PCO, but there are. And due to presence of this term, this is actually going to make a contribution, non-zero contribution. So now I have to tell you about this cubic vertex. So this is a part for stream vertex, and Barton gave very beautiful lectures on this for the last 2 days. So I can be quick. So it includes, choice of local charts around the, in this case, open string punctures, together with some, range of the moduli space. And in superstring, there's extra things. So the extra thing is the choice of PCO locations. This is also part of the data specifying the stream vertex. So you can think of the, Barton drew this like fiber over the moduli space that in this case not only involves the choice of local charts, it also involves the location of the PCOs. So let's consider the cubic case with 3 NS operators at the boundary. So in the upper half plane Z, in the upper half plane Z, this is where we put the operators as usual, 0, 1, and infinity. And I'm going to use Sen's local charts. So these are the local charts. W's are the local charts. And for example, this W0 is around this 0, and this alpha and gamma are the stream field theory parameters. And alpha is typically taken to be large, even though Nathan and my computation, we could carry it exactly in alpha and gamma. And when alpha is large, basically you can see that it covers smaller and smaller neighborhood of this puncture. So it's roughly the stub parameter. And we have to specify the location of PCO. So let's say we fix it somewhere in the bulk. Why? If you want to respect the permutation symmetry, then you can put it at the cubic root of unity. But we are just going to carry Y label from now on. And with that, we specify the cubic vertex. We can explicitly compute this cubic vertex where one insertion is ghost zero mode and the other 2 are the translation 0 mode. And we just do the computation, take the square of the cubic vertex and multiply by 2, which is the propagator, and we get this thing, which depends on the PCO location. This is because ghost zero mode is also conformal primary of weight 0. So this is the contribution which we had to add by hand. Okay. So we are done with 3-point vertex. Now let's go to 4-point. So first we have to discuss the propagator region for 4-point. by which we mean, we are doing this plumbing construction where we glue the local charts around the, say, punctures at once with each other. And this Q is a plumbing parameter. So we get one parameter family, one real number parameter family of new Riemann surfaces, this with 4 punctures. And depending on which SL2 transformation you do, you get ST and U channels. For example, in S channel, we can put punctures at 0, 1, and infinity. And the other location will be now function of this plumbing parameter Q. And as you can see, when Q goes to 0, this nears this 0. This is not all that we are getting, because this also induces the locations for the PCO. So we originally had PCOs here. Now, after this plumbing and with SL2, in the S channel, we have these PCO locations. And essential point of this PCO location is that they depend on the moduli parameter, the plumbing parameter here. And this will come back to us later. Okay. And we can do similar for T and U channels. And our convention will be that this Y1, S, Y1, T, and Y1, U are the ones which approaches this thing, the integrated vertex operator, as we take Q to be 0. So what's the picture? So this is a picture that Barton drew several times. But for our case, because all the 4-point insertions are on shell, we are actually not going to bother about the specific local chart choice for the 4-point vertex. Instead, what's going to matter for us is actually this another direction in the fiber, which is the location of the PCO. So I drew just one line, but it's actually D2 times D2 because we have 2 PCOs. Okay, and this x-axis is the moduli parameter. So around this S channel, T channel, and U channel, we did the plumbing. So we have naturally induced location for PCO, this blue line. Okay, and basically choice of 4-point vertex in this case amounts to choosing this whatever you want for this green line. You can choose it like this. You can choose it like what I've drawn here. And important point is that you shouldn't have a gap. Okay, you shouldn't have something like this. If you have a gap between propagator region and vertex region, then it's going to lead to inconsistency of your string field theory reaction because it's going to be not gauge invariant, and those states will not decouple from the on-shell amplitudes. So it's important that they match at the boundary. So I presume that you can just work with some generic choice of such PCO locations and show that it's independent of how you choose this curve to be. But Nathan and I realized it's a bit cumbersome to, in practice, work with such arbitrary choice. So we decided to do something more simple. So this is what it looks like. So let's look at this orange part, which is the vertex part. So this is where we have to determine where the PCOs are located. So in this entire region, we are going to put the PCOs at some fixed location. Okay, both of them are at fixed location. But we are going to do a bit better. So one of them, we are going to put at one y1, s evaluated q equals 1. The other y1, t evaluated q equals 1. So these are the locations of y1, s at this boundary and y1, t at this boundary. Okay. So this PCO location at least matches for the first PCO at the boundary where they meet the propagator region. Okay. And this y2 matches the PCO location of this y1, t at the boundary where they meet. So the only different PCO location, for example, on this place is y2, and on this place is y1. And you can basically run the same business for T and U channel, and then you can do it symmetrically so that now we can focus just on this yellow region. So, because the PCO locations jump, at least one of the PCO locations jump between propagator region and the vertex region, we have to also introduce this vertical segment. Okay, and this is the by now very familiar story, which is vertical integration discussed by Sen and also Sen and Mitten. So I want to tell you that this is not necessary for us. We could have just chosen this type of some smooth choice for us because we don't need to worry about spurious singularity for this simple computation. But actually, this computation is quite cumbersome, which is the reason why we decided to choose the section like this, which is actually way easier and way more manageable. But I mean, when you think about possibly computing open string amplitudes at some higher genera and so on, there will be spurious singularities, and this type of vertical integration will be required. It's not a choice. Okay, but here is a choice to simplify the computation. So I wish to highlight more on this partial Xi term. because that's where all these PCOs and issues come in. So typically the Beltrami differential we introduced for bosonic string involves this Beagles term. Okay, we compute the correlator and then we integrate over the moduli space. The integrating over the moduli space is coming from this Beltrami differential. So here this dt is the moduli parameter. But in superstring, we are now very familiar with the fact that there's extra term which carries this d xi, partial xi. So here y alpha is the location of PCO. Okay, this 1/, PCO means that we are eliminating that PCO and instead we are plugging in this expression. Okay, so we have partial xi instead of the usual PCO computation. And as you can see here, here's partial y over partial t, which stands for the moduli dependence of PCO. So this term makes contribution when there is explicit dependence on the moduli for the location of the PCO. And this term, for example, can be easily derived once you fix the Walsh gravitino profile to the once you gauge fix the Walsh gravitino profile to the delta function supported. But somehow I find that most of the standard textbooks on string theory actually do not even discuss like this type of details. So okay, what is the effect of this term? So first, in our case, in the propagator regions, this PCO locations depended explicitly on the moduli Q. Okay, so that's basically this term. This term is non-zero, and this term must be included. And secondly, we saw that at the boundary between propagator region and the vertex region, PCO locations jump. Okay, this was represented by these red lines here. So in that case, we have even easier computation. We integrate this partial xi is a total derivative, so we get xi y final minus xi y initial. Okay, so with all this equipped, let's go and compute things. So first in vertex region, we specified the location of 2 PCO, so we can simply plug it into our previous naive computation, and we integrate over this finite region in the moduli space, so there's no divergence, and we get this type of answer. But again, I want to emphasize that Nathan and I have the full answer. It's just too lengthy to provide to you. But if one just explicitly plug this expression into the Mathematica, it's going to spit out some answer. Okay, but here we are just for the sake of the presentation, I am presenting the large alpha limit only. So that was for the vertex region, and now let's consider the propagator region, which are these blue parts. Okay, so again, these PCO locations depend on the moduli parameter. So in addition to usual Beagles term, which is this one, we now have to add this partial xi term. Okay, together with how they transform as you vary the moduli. So for the moduli, we are going to use this prolonging parameter. We know x and q, like how they relate to each other. And we simply integrate this thing over this propagator region, which is in terms of the plumbing parameter is from 0 to 1. And again, we can get the exact answer, which in large alpha looks like this. Okay. And don't forget that we actually have also contribution from both zero mode, which we had to add by hand. So that's actually coming in here too. And to be precise, okay, this is a computation for the propagator region, but from the effective action point of view, this is actually contribution to the part of the effective vertex, because effective vertex includes the terms where you integrate out the massive modes, which is exactly this computation. Okay. And now we have to fill in this gap. Okay, and this vertical integration is what it is. So instead of one PCO, which is moving, which is jumping from here to there, we now have to insert this zygote. Okay. Again, this is computation which one can do. I mean, there's no integration. I mean, there was integration, which was integrating over partial xi, but we've integrated it and got this xi difference. And this is the answer we get. Okay, we get it for this left S channel part and right T channel part. Okay, so we have exact expression for all of this. And now we add all of this for this yellow line, and we correctly get 0, okay, as expected. So I wish to emphasize that, I mean, we already know this lesson that in string field theory, I mean, as long as there's nothing going wrong physically, we shouldn't run into any divergences and everything should be finite. And that's what we see here. So let me finish with the outlook. So I told you that this was actually motivated by our other project, which is work in progress, which is about basically this 4 graviton scattering in type 2b, which she mentioned. So in the bosonic case, our friend Ashok has, in series of beautiful papers, he basically did all the string field theory computations for the Seiko-Swan case. Yeah, thank you. And we have the answer now, up to factor of half. And in our current computation for type 2b, we have the ingredients for, we have the results for each of the ingredients, but somehow we are still missing some factors of 2 and 4, and we are having some hard time canceling off the string field theory parameter. So it's still work in progress, which we have to finish. But another message that I want to convey today is the following. So we see that, in superstring, all these things like PCO, partial Xi, and vertical integration, they matter. String field theory community is already very familiar with this fact. But when you consider that, hardly none of the standard textbooks even discuss this partial Xi or, vertical integration, maybe it's good for us to get refreshed that, maybe it's good for us to let other people know that these things matter. So at some point in the past, she actually suggested that, what if we actually come up with some, honest computation involving this type of things? For example, higher genus. So, vertical integration is absolutely necessary when we run into superior singularities, which starts to arise when you consider, say, torus 2 point with 2 NS punctures. And there can be some, cheating one can do. But what if one go and do the honest computation and see, the essential role of all these ingredients of superstring field theory? With that, let me end my talk, and thank you for your attention.
So thanks a lot for your nice talk. So if there are questions, please raise your hand on the chat. Let's see, I can see there is some raised hand from Nathan Benjamin. So please just go ahead. Oh, there is no more there. Okay, so now there is only, I think there were 2 raised hands, but now there is only 1. I cannot see it actually. So please, the one who raised the hand, just make the question.
Yeah, so the computation that you did is like, so the computation is that you did is the 5-4 in a D instant on Bragg, right? I understood correctly.
Right.
So that answer you finally got to be 0, means after doing this particle integration to do the computation. So is there any independent way to expect that this should be the result? Is there like a check that this result is correct? Because you did the particle integration, which you didn't need to do. This probably for computational simplicity, right?
Oh, okay. So so there are 2 points I want to make. So first is that, again, vertical integration was not necessary for us. It was just a choice to make the computation simplified. But this partial Xi contribution is absolutely needed, and string field theory in this context is again needed because the usual unshelled computation will be ignorant about this ghost 0 mode issue, which can be fixed only after you introduce proper gauge, where you set the anti-fields to 0, which is different from single gauge. So that's the first comment. And second comment, whether there's another way to derive that this is 0. This is our very natural expectation because these are moduli modes and we don't expect any effective potential for this. So I would say it's a very natural expectation. So physically, this is not interesting result at all. It's just what we all know and what we all expect. So it's not interesting physically, but I just wanted to say that this actually already manifests the fact that, lots of ingredients in this superstring field theory is actually necessary for computations like this. And in a more complicated computation for closed strings, these are just essential parts of the computations. Yeah, thank you.
Okay. Yeah, thank you.
Yeah.
Are there other questions, other raised hands?
Yes, I would ask a question. Minjae, very nice talk. Can you show your diagram again of the vertical sections and all that stuff?
Yeah.
Further, no, even more. Yeah, there. So
this one.
This one, yeah. So how canonical is that part of the section where you go up, horizontal, and up again? Is it completely canonical? Like, could you have the two punctures, the two PCOs vertically integrate simultaneously and then just hit directly the other one? Or are there choices in what you drew?
Good. There's no canonical choice. And the later thing you mentioned is also perfectly fine. It's just that you have to add another partial side term for, simultaneously, like the jumping of the other PCO. That's perfectly fine. So yeah, there's no canonical choice. And just like, choice of string vertex, this is, your choice, as long as there's no gap. Yeah.
I see. So let me suggest a silly canonical choice. I don't think it works, but you have the PCO positions initially and final in those two cases, and think of a hyperbolic metric in the disk and move them along geodesics. Could that work?
Oh, I see. So here's one thing I want to mention, which is that, actually the result of vertical integration do not depend on how, like the path you are moving them. And this is actually very essential for the superstring field theory. So whether you move it along geodesic or some other complicated path does not matter, because the only thing we care about is its initial and final position. Because if you see,
okay, so you're saying the off-shell amplitude doesn't depend on the trajectory you use to move the PCOs?
That's
Even
right, that's right.
I see.
Yeah, so that's because we are simply integrating over this partial xi term, and this xi, this is total derivative, so it's simply integrated to this expression. Yeah, and this actually is a very important point, because in some higher genus case, these spurious singularities that we know are actually complex codimension 1 in the moduli space. So generically, if you want to, pass through them, you are, destined to hit the singularities. But the very fact that this vertical integration depends only on the initial and final position, in a sense, saves you from that.
Yes.
Yeah.
Okay. Thank you.
Thank
very
you.
nice observation. Very nice.
Thank you very much.
I have a comment.
Yeah, sure.
Sorry, I don't know how to raise my hand.
No problem.
So the independence of the path of the PCO only works if you have one PCO, if you're moving one PCO at a time. If you're moving two or more, then it matters.
Right. So you have further gaps, like higher codimension gaps, and then you have to fill in the gaps. And that is exactly explained in beautiful blurry detail in Sen and Witten's paper in 2015. Yeah. Thank you for the comment.
Okay, so I guess we have no more time for other questions. So I also had a small comment, but I can keep it for the discussion session. So I think it's time to go to the next speaker. And so who is Atakan Hilmi Firat from MIT. So can you please share your screen? Okay, very good. Okay, so he's going to tell us about initial value problem and causality in string-inspired non-local field theory. Please go ahead.
All right. First of all, I'd like to thank the organizer for inviting me and giving the opportunity to talk about my work. So this is a work in progress. Hopefully will be out soon with the collaboration with the Harold Urban and my advisor, Martin Sliba. So here's my outline. So first I'm going to talk about why we are considering the theory that we are considering. Then I'm going to tell about how to do field redefinition to get rid of non-localities and give us make the initial value formulation manifest. Then I'm going to use the methods we developed to investigate how the rolling tachyon solutions get redefined. And then I will consider the case where I have a covariant theory instead of a just time-dependent one. Then I will make some comments about the dispersion relation for signal propagation and conclude. So our main goal is that understanding how we can give an initial value formulation and understand causality in string field theory. I mean, this is a hard question. So because we know that the string theory and string field theory contains this non-local interactions in terms of like e to the some derivative square type of interaction. So instead of dealing, to understand the heart of the issue, we are going to consider a toy model where we just have a shares this non-local feature of SFT, but ignoring all the other junk that we have in the theory. So we will consider just a tachyon in the open SFT, and that will lead us to this theory. So I'm going to take here everything to be dimensionless for simplicity, and the psi to be our non-local parameter, which is essentially going to be some logarithm of some mapping radius. Well, in the case of within SFT, it's the log of this usual 4 square root of 3 over 3 number. And we're going to consider this theory and try to understand how we can give an initial value formulation to this. So if you naively look at this theory, you see it contains infinite number of derivative interactions, higher derivative interactions. And if you write the equation of motion, you will see that it will also contain infinitely many derivatives. And when you try to give the initial value formulation in some Cauchy slice, you will see infinitely many data. At some point you ask, well, this doesn't make sense. So in order to get rid of it, we are going to try to do some Firat definition to establish some perturbative scheme where we can eliminate higher derivative interactions and then reduce the number of derivatives in this action. So here's the potential for this. It will be useful later. So it says a stable vector and a tachyonic vector, and that's the usual cubic potential. So like I said, we are going to try to eliminate this higher derivatives perturbative link psi square. That will be our perturbative scheme. So the theory just so I'm going to take just a purely time dependent situation for simplicity at first, which will give this expansion for the Lagrangian. And as you can see, there's an interaction contains second derivative. There's an interaction contains 4 derivative. So as an example, I will eliminate this with some Firat definition to establish how we can get rid of this higher derivative terms. Then I will do the general proof. So imagine I perform the following Firat definition, where I do the phi plus d phi, where this is not going to be infinitesimal. And then I consider this d phi, expand this d phi in terms of psi square, del phi 2, and higher terms. This will shift Lagrangian as follows. At the leading order, I will have other jump in the higher psi to the 4 and more orders. So as you can see, we will have an equation of motion, and I will also include the term that I want to eliminate. So by choosing this del phi 2 to be this minus phi square, I can see that this term can cancel this one, and all I left with will be this one. And if I use this prime denotes the derivative with respect to phi and expand it, this is what I got. And it excited to the square order, I see I eliminated this higher derivative interaction that I have. So this raises the question, okay, we can do it. So question that I want to ask, is it possible to put the theory of the form where I have a standard kinetic term, 2 derivative in time, and I have a potential possibly non-polynomial in psi square, and which shouldn't contain any derivative. And the first case is follows, but can we do at the higher order after performing some Firat definition like this? And the answer turns out to be yes. Yeah, we can do it. So it seems that at least perturbatively, I can choose this del phi 2, del phi 4, and all the other higher Firat definition, and just get rid of this exponential in exchange with some potential. Okay, so let me give the proof, because I already did the base case, and the proof will proceed with induction. Suppose I eliminated all higher derivative interaction to some order, and I perform a Firat definition at next order with some unknown Firat definition. And this will shift the Lagrangian with the usual, the first L0 term, which is just the kinetic term and the potential. There will be the dt derivative free terms in the lower order. And at this order, I will have this. again, I have an equation of motion. There will be other terms, but I don't care what they are. But in addition to the usual derivative interaction that I'm get from the exponential, I get additional terms that are induced by the lower orders that I previously ignored. So I will put a prime here to denote there are extra terms. And the first thing that we can notice is that if a term in this L2K prime can be written with the second derivative of phi times some function of phi and some derivative of phi, I can pick, I can include this x to this Firat definition and basically redefine this term as follows, where I reduce the number of time derivatives that I have. So that raises the question, like if I can am I allowed to put every term in this like L2K prime of the form after possibly Firat definition multiple times, integration by parts, and repeat this procedure to get every derivative? And that's the second part of this inductive proof, where we show that we first take the generic term in L2K prime, which will be of this form. Well, I have higher derivatives, with which I mean the derivatives have orders greater than 3. And I already eliminated dt squared phi because I know that I can. And I have first derivative to some power and the usual polynomial to some power. This will be generic term in this. So you can see I can integrate by parts, and this will be what I will get. So here one of the terms I get dt squared phi again, which I can do a Firat definition to replace with minus v prime phi, which will just contain phi. And if you do that, I see that I can eliminate the leading one, the leading power of the derivative k1, which I will call lowest order, by 1. So we see it is possible. And doing this recursively, it is clear I can reduce to its lowest possible value, 3, if it is not. And after which I can do one integration by parts, like here, like consider k1 equals 3 here, which will be dt squared phi here. And I can do the Firat definition to that to get rid of this term completely. And this shows that I can recursively, by doing integration by parts, Firat definition, I can get rid of all of these terms and reduce index 1 by 1. And this shows after I do that, the terms of the form as follows. So as it is, we see that there will be initial value formulation because I see that I can reduce every derivative to the first order derivative to some power, which will make, when I write the equation of motion, which will make and if I repeat this to the all orders in xi squared, specifying phi and the first derivative will be enough to give a initial value formulation and causality manifest. But we can, since this is just a purely time-dependent theory, we can actually do more, which I mean that I can do an integration by parts for one of those terms, like this, and expand this derivative to get this answer. We will have this dt will apply to this and also apply to here. But we see that the second term is actually going to be the first one, which means I can carry this out, simplify, and get this, which will contain the second order derivative, which I do a Firat definition and replace with this. So I can even do more and get rid of this first derivatives as well. And what I will left with is the most generic term, which I started here, can be reduced to some potential term after suitably choosing the Firat definition and integration by part. And by induction, I can say that the non-local theory in 0 + 1 dimension, the case we are considering, can be turned into the standard 2 derivative theory with potential, at least perturbated in psi squared. So the result that I got after we do this algorithmically, we find that the resulting potential is this. As you can see, it will contain terms of psi squared, psi 4, psi 6, and the same here. And the Firat definition we have like this. So before I go on, I want to do some remarks. I see some raised hands. Is it okay if I answer your question after the talk?
I think we should postpone questions for at the end of the talk. So I would suggest you just go ahead, and then Igor can ask his question after you finish your talk.
Okay, so I want to do 2 remarks on this potential. So this potential turns out to be not unique. There is not a single theory we are mapping after this procedure. And the easiest way to see is as follows. Say that I consider this theory definition where C is some real constant and I have this dt phi square v phi. And if I apply to this order, I will get this. You know, I have this and the equation of motion. And I will have other terms in the next orders, but like since I'm working perturbative link psi square, I don't really care. I will deal with them later. And if you expand this term, you will see this 2 terms turns out to be a total derivative. And the cross terms, this one and this one, turns out to be another total derivative, which I can ignore. So what I will left with will be another potential term. And if I expand, this is the case here, this will be the case, plus other stuff at higher orders. And in fact, this can be generalized. You know, this is the general theory definition one can perform. And each, you know, you will see that if you expand the terms with the equation of motion, things will be total derivatives, and you will end up with just a potential term emphasized to the 2K. And again, like I should emphasize, we can deal with this ambiguities at each order and deal with the higher order in psi square in the higher when we encounter them in the next order. So this set of theory definitions seems to cover all ambiguities, although we didn't prove this, but it seems very likely because we couldn't find any ambiguity of this sort. And since there is like this, since this construction works for any type of constant we have, we can just say, okay, you know, by choosing this SC and case, we can put the potential in a nice form. Say, and the one form that we work all the time is that where we specify the C and case to make the odd terms in this potential polynomial instead of some series in psi square. So we will call this canonical form, and here's the numbers. So the other point that I want to make is that the depth of the critical points of this potential shouldn't change, right? Because it's observable, and we see it indeed it doesn't, because you can see the theory definition can be written as some part just depending on the phi's, and some part contains the phi's and its derivatives. And the only thing that is independent of derivative after you do this theory definition will be variation of the original potential by of just g of phi. And this shows you this gives you the formula for it, and shows that one of this v tilde phi, depending on psi square, is just a theory definition of the original potential, which shows that okay, the depth doesn't change. And we check this perturbatively to the psi to the 8, I believe. And yeah, so this is the part we take. We just take the non-local theory, we prove that perturbatively in psi square you can do a theory definition to get rid of the exponential perturbatively. Okay, so next we investigate how the rolling tachyons will map, how this theory definition affects the rolling tachyon solutions. So usually, this is a usual story. We just write the equation of motion, and we start with the unstable at -infinity and roll down to the stable one, and by choosing this answer. And this has been done like in the case of chaotic strings, and but also in this theory as well. And we get some recursion relation which one can easily solve. And as a common in this type of non-local theories, we get this unbounded oscillation. So we start with 0, but we roll down, we go over the turning potential, and we go back, and there's an even bigger oscillation, and they just keep on going in this original formulation with exponentials. And we give some semi-rigorous argument that the solution converges for all psi square, and the time we draw will give a nice approximation to the solution. But since we're working in psi square perturbatively for theory definition, it is a better idea to work perturbatively in psi square, but exactly in time. And so in order to do that, we take this approach where I consider ansatz in psi square instead of like ansatz of this form, and just substitute this to the equation of motion and write the equation order by order. So the first equation will be, unsurprisingly, rolling in this cubic potential for the local theory, which can be solved by energy conservation. And here's the answer. And the second one and the higher ones will be some linear, second order, nice ODs, which you can plug into Mathematica and solve by knowing the previous one. For example, you can solve this by inserting this expression for phi 0 and just copying this derivatives. And it's very simple thing to do. And this, after we do that, this is the solution we get. We have we have much more terms. And the solution in this case will look like as follows. The green one is that the usual local rolling. And if we add more orders, we just produce those big oscillations. And compared to the non-rolling solution, we know that is the correct solution, the exact solution in psi square. It approaches, and we investigate more higher orders that this matching is actually getting improved. So from this, we expect that including all orders in psi square will produce this red dashed line curve here. So, but the advantage of this, we can do a Firat definition, and we will have just a single expansion, and we can get a well-behaved, the series wouldn't interfere with each other. So this is what we do. So we consider our Firat definition, where I will take phi to the original solution, where we have exponential, and phi prime to be our redefined solution, and basically, inverting this relation and, putting phi, the solution we find here, into here. We get the following, and this looks like, compared to the usual rolling of the potential, it looks like this. So as you can see, the blue one is that the one we get after Firat definition, and the red dashed line is that the numerical rolling we did for the potential we had. So it seems it has provided a very nice match. And actually, if you include more orders, this match improves here as well, and nothing goes beyond the turning point. So this shows, like I said, this shows there's no overshooting or oscillation after Firat definition. And it suggests that the using the original formulation is kind of using the wrong Firat variable, and kind of makes the physical aspect of the rolling problem non-manifest. But after Firat definition, it becomes much more well-behaved, much more palatable to us. And like I said, including more orders will improve this behavior. We check the very high order, I think psi to the 16 or something, and the full, based on the argument that I have, that it seems that the full rolling solution will map to the rolling solution of this potential exactly. And we also, like I said, this potential was ambiguous, but we checked that using other form of ambiguous potential, actually, and they are for their suitable variation. This story also holds in those potential, which gives us some consistency check for our procedure. Okay, so this is the rolling case. Now I want to back to the covariant theory, where I consider in the D+1 dimension. And here is this again. Here's the expansion. And using the arguments that I have before, I can show that I can reduce the Lagrangian as follows. But now I have two issues. First of all, I have this term d phi to the 4, which is the d phi square. So it's not possible to refine this term because the analogous formula that I use for the first derivative doesn't work because the Lorentz indices are contracting and you don't get the same term.
We still have 5 minutes.
The right-hand side. So, but like I said, this is fine because I can just keep it. Like I said, this is just first order in derivatives. But the other problematic term, this is the pink term, which we call obstructed term. It is not possible to redefine because you cannot put them in this form manifestly. So by breaking the manifest Lorentz covariance, we can actually redefine this term. So it's kind of seems like there's a tension between the things that we can keep while keeping the Lorentz invariance versus things that we should be doing when we are trying to make the initial volume problem manifest. And after do this is what we get. So it will induce some potential. There will be some higher derivative in spatial, but it will be at most second order in time. So that will be a good initial volume problem. Alternatively, we can focus on light cone. I will be very quick here, where you can just restrict to the light cone time and try to redefine the keeping non-locality in the transverse direction. And this is also, we show that this is also possible. And the arguments here can be repeated to all orders in psi squared. And this is very easy to show based on previous arguments. Lastly, I want to talk about the dispersion relation. So main idea here is that linearize the equation of motion around their non-trivial background for the massive case and tectonic case, and just write the dispersion relation, which you can read off the refractive index. And it turns out there is an exact solution that you can get in terms of this something called Lambert W function or product law. And the effective masses looks like this. Maybe I should be there to see that the full formula. So in the massive case, there is no problem because we see that it's kind of interpolating from -1 to 0. But in the tectonic case, we have some decay in the signal propagation because this imaginary part develops. So the reason that we do that is that we can then look at the infinite frequency limit for the refractive index or inverse power of it, and look at define something called wavefront velocity. So the wavefront velocity is the correct notion to describe the causality in the signal propagation. Not, sometimes people say it's group, it's not a phase velocity. Sometimes people say it's a group velocity, but the exact notion is this wavefront velocity because it describes how the if I think like a snap, how it propagates into the other somewhere far away. And in those both cases, the important point is we found it's bounded by 1. Like it's despite the non-localities, it seems that the signal propagation doesn't contain any causality. So last, I would like to conclude and the open questions that we have. So we argued that it is possible to theory refine a non-local theory to a standard two-derivative theory with some caveats that I'm going to mention. And that this tames the oscillations of this unbounded oscillation of rolling solutions in non-local theory to something, some classical rolling solution, Newton's second law. So the caveat that we have, first of all, everything we did was perturbative in psi squared. So you can ask, okay, is it converging? I don't know. Is it immutable? This is the most important part, because if it is immutable, there may lose some degrees of freedom, which is kind of dangerous. But yeah, we should admit that we don't know the answers of these questions yet. Relatedly, is there work non-perturbative in psi squared? And relatedly, is there like an exact form of this potential we define? Like, is there a closed form expression so we can do even more stuff? Maybe like choosing this C and K ambiguity correctly, or doing something like that. Is there a formulation where I can make the Lorentz symmetry and initial order problem manifest at the same time with some additional field with some gate symmetry? Is it possible? And how does quantum case work? So there's this, and everything I did was classical, so that's another thing. And we want to relate this to the usual approaches of causality in quantum field theory and like a micro causality or this very unappreciated condition, Bogdan's condition on the S matrix. This is open. And our final question is how it relates to SFT. How can I lift those? How can we lift those results to the full theory itself? So thank you for listening, and yeah, this is what we did.
Okay, thanks Atakan for your very nice talk. So we have time for questions. I think now, Igor, if you are still there, I think you can ask your question.
Yes, I'm here. So I think the problem is interesting, but I think the problem is very interesting, but the way you are approaching, I think, will not work, and I'll explain why. What you are doing is with an infinite number of derivatives, so it should work also with a finite number of derivatives, okay? Then, when you have a finite number of derivatives, you run into a problem called the Ostrogradsky instability, which is a well-known problem with higher derivatives. And this means that there is no way of making the theory stable. It will always collapse, because essentially the Ostrogradsky instability is the existence of non-existence of a vacuum, of a ground state. So you cannot avoid this problem, and as soon as you switch on interaction, everything collapses because of entropic reason. It is more convenient to produce particles and sink. So I don't really think that this approach this way will work, and this is the reason. So
okay, we are aware of the Ostrogradsky formalism, but the one thing that we can say that the perturbative parameter, so there will be now no chi-square in those theories. There will be no analog of that type of term. So if you try to do that, at some point you will presumably encounter some issues in terms of how to do this, how to do this perturbative, because we have this nice chi-square that we can do perturbation on it, but in those theories, I don't think that we have that sort of a parameter that we can use.
Yes, but the point is that the Ostrogradsky is instability is well, you can also recover it in the perturbative way, but it's clearly a non-perturbative issue. You have a ground state. You can find probably solutions which are stable and so on, but at the end, the system is not stable.
That's correct. But the one catch is that the Ostrogradsky formalism doesn't work for the infinite number of derivatives.
Yes, because but the way you have presented, you should work also with a finite number of derivatives. This is the reason why I'm doubting about the way whether it works or not.
Yeah, that's a good concern. But like I said, since we don't have an analog of this chi-square parameter, I don't know if we can set up this perturbative type of argument for it.
Well, you will see.
I think we can postpone this nice discussion, these nice points for the discussion. We will have more time and we can discuss them with more. So now we still have a couple of minutes. So there is another raised hand by Debashish Ghoshal. So please go ahead.
Yeah, hi, can you hear me?
Yes, we can hear you.
Yes, nice talk. I just have, I actually want to ask more questions, but I'll ask only one. But before that, I want to just make a comment on the previous comment. I think the infinite derivative case is really very different from the finite number of higher derivative case, because the way he was solving it, he was postponing the cancellation to the next order and so on at every stage. And that you cannot do with a finite number of higher derivatives, but this process with infinite number of derivatives, you can keep continuing. And these two cases, I think, are really very different. It's not that their formalism will apply to higher derivative with finite order. Maybe Hirat, maybe you can, Firat, you can correct me. But my question exactly is about a different issue, which is that we heard these lectures by Olaf the last 2 days, and he was talking about this morphism of two theories and this homology transfer. So what you do about the equivalence of these two theories with higher derivative and the other with this redefined theory, can it be understood in that formalism as well?
Well, this is an excellent question. Because in some way this might be related to this, since which say that I tried to set up some L-infinity framework for the higher derivative theory with some higher brackets as interactions. So maybe one can do it, and the procedure we described, maybe giving realizing this this stratification and the mapping to the DG Lie algebra, but still, this is an open issue. I'm just speculating here. Maybe it's there may be some relation between those two.
Okay, thank you.
or like some, not necessarily strictification, but like realizing some sort of a L-infinity morphism where you map to the each higher brackets to the other type of brackets.
Thank you.
Okay, so I think it's time to pass to the next speaker. So thanks, Atakan. And so our next speaker is Kasia Budzik, from Perimeter. And okay, so she has already shared the screen. So the title of the talk is Conformal Defects from Open String Field Theory. Please go ahead.
Okay, thank you. And thank you to the organizers for the opportunity to speak here. So this talk is based on a paper in collaboration with Mirosław Rabczak and Jairo Rojas. So I will talk about a method of finding conformal defects based on open string field theory and level truncation. So conformal defects appear in physical system as the low energy limits of impurities. There is a special type of conformal defects called topological defects, which are especially interesting since they implement symmetries and dualities. They can be used to constrain bulk and boundary RG flows, and they realize mathematical concepts such as fusion categories and modular tensor categories. So in general, finding all conformal defects in a given 2D CFT is a very difficult question. And unlike boundary conditions, conformal defects are only classified for the Ising model and the Liang model. So one can try to find new conformal defects, for example, by defect RG flows, all trying to find defects which preserve some extended symmetry. But we also know that open string field theory can be used to search for new conformal boundary conditions. And this can also work due to the folding trick. So in this talk, first, I will review some basic facts about boundaries and defects in minimal models. Then I will talk about defect RG flows, and I will focus on this example of a topological defect in minimal models, which was studied by Kormos, Runkel, and Watts. Then I will talk about open string field theory and its classical solutions, and apply the level truncation method to conformal defects. And then I will mention some future directions. Okay, so minimal models are a special type of two-dimensional CFTs. We will focus on unitary minimal models with diagonal partition function. So their Hilbert space is given by a finite sum of irreducible highest weight representations of the Virasoro algebra, which are also called conformal families. And in minimal models, they are labeled by Katz labels, which are these two integers which belong to the Katz table. And for unitary diagonal minimal model, the central charge and conformal weights of the primaries are given by these formulas. Okay, so next we can consider a CFT defined on a manifold with a boundary. So boundary conditions for bulk primaries are represented by boundary states, which we denote by these two cats. And boundary states encode the one-point functions of bulk primaries, all bulk operators in the presence of a boundary. And these boundary conditions have to satisfy some consistency conditions. So for example, we say that the boundary is conformal if it is preserved by the conformal transformations which do not displace the boundary. And this condition translates to this requirement on the boundary state. Then there is another condition called Cardy condition, which comes from the consistency of the theory on a cylinder. So you can view the theory on a cylinder with the boundaries in two ways. First, as an open string propagating along the strip with two boundary conditions, and also as a closed string propagating between these two boundary states, which gives us this matrix element here. So this is a non-trivial condition on the allowed boundary states and their boundary spectrum. So in case of the diagonal 2D CFTs and the non-diagonal minimal models, these consistency conditions have been solved, and the solutions are called Cardy states, and they are in the one-to-one correspondence with bulk primaries. So we can also label them by the Katz labels. And the boundary spectrum of such a boundary state is given by the fusion rules. So for example, for a boundary state with a Katz label RS, then we look at the fusion rules of phi RS with phi RS. And the cut labels, which appear here on the right-hand side, give you the boundary spectrum. So I'll quickly review the easiest example, which is the minimal model with m equal 3, which describes the continuum limit of the critical point of the 2D Ising model. So this is the cut table. So there are 3 primaries. So therefore we have 3 boundary conditions, which in the Ising model correspond to the spins up, spins down, and the free boundary condition. And to get the spectrum, we look at the fusion rules. So for example, sigma sigma produces identity and epsilon. So that's why we have these 2 conformal families here. Okay, so now let's go to the conformal defects. So due to the folding trick, that conformal defects in a CFT are equivalent to conformal boundaries of such a product CFT, where this bar here means that the holomorphic and anti-holomorphic dependencies are switched. So we also have that the defect spectrum here is given by the boundary spectrum here, and we can define the defect G function as the boundary G function here. And the boundary G function is just defined as an overlap of the boundary state with the vacuum state, which is also equal to the identity expectation value of the identity in the presence of the boundary. So one may now think that since the conformal defects are just equivalent to conformal boundaries, then we should be able to classify the conformal defects. So this is not the case because the sphere is usually not rational with respect to the total Virasoro algebra. Sometimes there is a case where if there's some extended symmetry, then maybe the sphere might be not rational with respect to the Virasoro algebra, but it might be rational with respect to some extended symmetry. And then you can try to find the subset of defects which preserves this symmetry. So there are also 2 types of defects which are easier to study. The first ones are factorizing defects. So these elementary factorizing defects correspond to just products of 2 boundary states. And in general, you can have a sum of such boundaries. And the correlation functions of factorizing defects factorize. And the second type are topological defects, which I mentioned before, and they can be continuously deformed as long as you don't cross any field insertions. And in minimal models, they are also labeled by cut labels. And the defect fields are in the representation of 2 Virasoro algebras, so they have 2 cut labels. And for the Ising model, we have 9 elementary defects, factorizing defects, so different products of the Ising conformal boundaries, and we have 3 topological defects. Okay, so like I said, there are 2 cases where we can classify all the conformal defects. So for example, the Ising model after folding is equivalent to the orbifolded free boson. So therefore we have 3 types of boundary conditions. There's the Dirichlet and Newman boundary conditions, which are parameterized by this continuous parameter. And some of the points on these continuous families can be identified with known topological and factorizing defects. And then the free boson also has the exceptional boundary conditions which survive the orbifolding. So these also corresponds to some conformal defects in the Ising model. And then the second case is the Liang model, which after folding is given by this non-diagonal minimal model. And the products of Liang and Ising and Liang and this minimal model also happen to be some non-diagonal minimal models, so interfaces between them are also known. Okay, so people also try to use other methods than folding to study conformal defects. So for example, we can try to study defect RG flows. So just like for the boundary conditions, the relevant defect fields have conformal weights which are smaller than 1, and then we can try to perturb a defect by such relevant fields and study the RG flows. So the beta function is the same as for perturbed boundary conditions. So these lambdas here are the coefficients of the relevant fields, and the only difference here is that these structure constants are defect structure constants, which in general are not known. So for topological defects, you can try to bootstrap them, which has been done in the literature for some cases. And also we can get some of these structure constants by this 3-dimensional topological field theory approach to 2-dimensional rational conformal field theory by Fuchs, Runkel, and Schweigert. So there is also another way to study conformal defects, which is called truncated conformal space approach. So this is a numerical method in which we try to find an approximated spectrum of a perturbed Hamiltonian. So the system that we study is a strip with two boundary conditions and a defect in the inside running parallel to the boundary. We can also map it to the upper half plane, and the Hamiltonian of such as a perturbed defect looks like this. And then we can restrict it to a finite dimensional space and try to find the approximated spectrum and other properties of the perturbed theory. So in particular, there is this paper by Kormos, Lungan, and Watts, which employed these techniques that I will now focus on. So they studied the topological defect with cut stable 1, 2 placed in minimal models. And this is what part of this spectrum of this defect looks like. So in particular, there are these two relevant fields. So they are chiral and antichiral with conformal weight smaller than 1. So we can perturb this defect by these two fields and try to find the fixed points of the RG flow. So they found the following fixed points, which I will now try to explain. So in the case of minimal models with m bigger than 3, there are six fixed points. So first of all, these 4 points here on the axis are all topological defects. This is because when you perturb a topological defect with a chiral field, you also end up on a topological defect. Then these 3 defects here, they can be found from the leading order perturbation theory. And then with the truncated conformal space approach, they also found these 3 points and they confirmed the existence of this. So this fixed point here is conjectured to be a factorizing defect, non-elementary. And this point C here is probably the most interesting because this one is conjectured not to be just a sum of topological and factorizing defects. So this is conjectured to be some non-trivial conformal defect. And then the case of the Ising model is quite different. We have a continuum of fixed points, and then some of these points can be identified with topological and factorizing defects. And the end of the flow depends only on the ratio of these coefficients. So the end of the flow for alpha is a defect which corresponds to the Dirichlet boundary condition in the orbifolded free boson. Okay, so basically these two pictures have been obtained by some combination of exact results and perturbation theory and truncated conformal space approach. So it turns out that we can get this picture also, but by very simple string field theory methods. So we will be using open string field theory. The open string field theory background is given by a matter boundary CFT tensored with a const boundary CFT with trivial boundary conditions. And the typical thing you do when you want to study properties of some CFT is to tensor it with an auxiliary boundary CFT with appropriate central charge. Then the classical string field is a linear combination of boundary operators of ghost number plus 1. And the action has this cubic form. And this 2 vertex and the 3 vertex can be computed in terms of a boundary CFT correlator of 2 or 3 boundary operators. Okay, so now I will focus on the classical solutions in open string field theory. So the classical solutions are conjectured to represent classical vacua, so either a tachyon vacuum or other d-branes which are associated to boundary states of the same closed string background. So what are the properties of these boundary states that are associated to the solutions? So first of all, we can compute the G function of these boundary states. So it is given by the action evaluated on the solution plus the initial, plus the G function of the initial boundary condition. Then we can also compute these gauge invariant observables of the string field called Elwood invariants. And then using Elwood invariants, we can recover the boundary states. So there are these 2 approaches to recover the boundary states. And the second one, it was shown that the coefficients of the boundary state are given by this Elwood invariant. And here the omega operator is an operator in the auxiliary boundary CFT with special properties such that this works. Okay, so now I will mention some of the analytic solutions that are known. So the first analytic solution was the tachyon vacuum solution. And then there's an important class of solutions which are correspond to marginal deformations of the original background. And then there's also this new solution which relates any two boundary CFTs that share a closed string background. So you need to know the initial state, you need to know the new state, and then some boundary changing operator between them, and you can construct an analytic solution. Okay, but in general, finding analytic solutions is very difficult, and it usually requires some new techniques. So especially when you want to find some new boundary conditions, then level truncation is a very tried and useful method. So a generic string field looks, for example, like this in the Siegel cage, and it has an infinite number of coefficients. So in level truncation, we restrict to fields with eigenvalue, which is smaller than some fixed level. Then we find saddles of the truncated action, and if they are stable under the increase of the level, then we can hopefully interpolate to the infinite level. And the level truncation method has been studied extensively in the literature, and some of the new boundary conditions, boundary CFTs that have been found are, for example, the honeycomb boundary CFT and some of the new universal sector solutions. Okay, so we will apply this method to this setup. So we start with this topological defect in minimum models, and then we fold it and get a conformal boundary in this product CFT. And then to get a consistent open string field theory background, we tensor it with an auxiliary CFT. And then to further restrict the number of string fields, then we restrict to a subset of the boundary spectrum, which is closed under OPE. So first of all, because we are only interested in like new boundary conditions here, then for the auxiliary boundary CFT, we just take the vacuum module because we do not want to excite some new boundary states here. And then here we take the subset of the boundary spectrum, which is generated by these two relevant chiral and anti-chiral fields, because in this case, some of the structure constants have been computed. Okay, so this is to show what string field truncated at level 1 looks like. So in this case, there are 3 components, and there are these 3 coefficients T1, T2, T3. So the solutions are written in terms of these components. Then the truncated action looks like this. And here we have the defect structure constants. So for this specific defect and for these specific fields, they have been bootstrapped by Makabe and Watts. So there are 8 solutions for minimal models with M bigger than 3. One of the solutions is always the tachyon vacuum. There is also one trivial solution, which corresponds to the initial defect. And then the other 6 solutions match the structure of the RG fixed points found by Kormos, Runkel, and Watts. So this is already at level 1. And now we can try to study some of these solutions to higher levels. So for example, this is the solution which is supposed to correspond to the defect C, which is the non-trivial new defect. So we plot the G function. And here on the x-axis, we have 1 over M, where M labels the minimal models. So this is the tricritical Ising, this is the tetracritical Ising, and so forth. And we plot the G function of the solutions for different levels. So we usually stop at level 4, and that's because in the OPE of these 2 chiral fields, at around level 4, there appears a new primary for which we did not bootstrap the structure constants. In the Ising model and tricritical Ising model, this primary is not there, so we can go to higher levels, and then we stop at level 6 because we're using Mathematica. But it is possible to go to higher level if you employ some better techniques, such as, for example, Matvei Kudryna can do. So this defect C is also achievable by the leading order perturbation theory. So we can plot the G function, the leading order G function. So this is the red line. So this is probably not a good approximation of the G function of this defect for low values of M. So we can see that at level 1, this is very close to the leading order G function. And then we suggest that probably the G function of the solutions at higher level is a better approximation of the G function of this defect. And we say that because we can also study the solution for the defect, topological defect 1. So in this case, we know the leading order perturbative G function, but we also know the exact G function because this is a known topological defect. So we can compare that again, the level 1 G function is close to the leading order. and then the extrapolated G function to the level infinity is a better approximation of the exact function than the leading order one for the low values of M. And the solution for the Ising model are different. So this is what the action looks like truncated to some low level. And there's this symmetry in the T2 and T3 coefficients. So we can check that the symmetry is still there up to level 6. So up to level 6, we get a continuum of solutions, which with the extrapolated G function 1.007, where the exact G function is 1. And then for this case, we can also compute one of the Elwood invariants associated to this bulk operator in the folded theory. And then this Elwood invariant varies continuously and it oscillates with level. And since we only have 3 values, we do not try to extrapolate because these Elwood invariants oscillate, but we can see that they get closer to the expected value. Okay, so to summarize. Oh, okay. Well, this is the last slide. So to summarize, the open string field theory and level truncation can be used to study conformal defects. And probably the most interesting thing is that already at this low level, you can recover the structure of solutions that you can get by the leading order perturbative analysis and numerical truncated conformal space approach and exact results. And then this is quite a general method, so you can use it for in the background if you know the its spectrum and if there's a finite number of defect fields below any level. And you need to know the defect structure constants, and there should be some sensible restriction of the string field. And this can be generalized to interfaces between different theories. And it would be interesting to find defects with a higher G function than the initial defect. And such solutions with higher G functions have been found by mathematical now, for example, in level truncation, but they require higher level analysis. And perhaps the most interesting question is that since we start with a CFT problem and then we end with a CFT solution, it would be interesting to see if there is maybe some boundary CFT analog or explanation of this method. Okay, thank you. You're muted, Carlo.
Sorry. Oh, yes, sorry. I was, so please, the first question is by Xin. Please go ahead. Thank you, Kai, for the very nice talk.
Thank you for the interesting talk. For people who spend more time thinking about QFT than string field theory, this approach sounds like trying to crack a nut with a sledgehammer. Normally one would approach this kind of problem with from the point of view of conformal perturbation theory, but of course the complication with conformal perturbation theory is that there's no systematic scheme for defining the notion of renormalized coupling and to identify the RG fixed point. Somehow you seem to get around all that issue using the string field theory framework with all these ghosts, which doesn't seem to have anything to do with the CFT a priori. So do you have some understanding of how the string field theory actually shed light on how to define RG in conformal perturbation theory? And I guess a related question is whether you can do this for the bulk RG flows, not just boundary RG flows.
So looking just at the level truncation, the papers that are known, then it's definitely easier to find the solutions which are very close, which are easily accessible from the RG flow. But also you are able to find solutions which have higher G functions. So this is was supposed to find more solutions than just the RG flow.
Maybe let me rephrase my question in the following way. Do you have a conceptual understanding of what is the role of the ghosts in string field theory compared to the approach of conformal perturbation theory? Why does the ghost somehow do the job?
I think this is a very good question, and I would also like to know why this works for these boundary CFT problems.
So perhaps I have a very quick question. So did you find in the solutions you found that represents conformal defects in this folding approach? So it is known that topological defects can be used to map solutions to solutions in open string field theory. So do you find examples of in the solutions that you find in level truncation? So do you find like pairs of solutions that may be related by the action of a topological defect?
So we would have to start from a different background, right? And so we will have to act with a topological defect on this defect D12 and start from a different background. And for other topological defects, we don't have many structure constants to this computation.
Yeah, so, okay, so you start with some, okay, so suppose you have your tensor theory where you do this folding trick, and then you have a topological defect in this tensor theory, let's say. Now this topological defect can be used to map solutions to solutions. So I was wondering whether the solutions you found in level truncation, some of them, maybe so there is some pattern in this solution, maybe if some of them are related by the action of a topological defect.
So I am only aware of this paper about string field theory and topological defects, and I thought that you can map these solutions, but then I would have to also start from a different background and find a solution there, and that's what I would map to.
Yeah, but yeah.
Yeah, so that's why I don't have anything to compare to, because this is the only background we started from.
Yes, yeah, okay. Maybe sometimes some topological defect don't change the initial background, but they just change the final background. It is possible, right? So maybe some group-like defect or something like that. Okay, I was just curious to know, so to see. So when you see this nice pattern of solutions, sometimes it's possible that there is some organizing principle. And okay. Are there other questions? So we are ahead of time, so we still have a few minutes. So I encourage questions from the audience. Otherwise, we can just stop like a few minutes before and take a somehow longer break. Okay, so now there should be like a 15 minutes break, right, Harold? Okay, so we can start again. Welcome back. And so now we have Ratul Mahanta from HRI, who is going to tell us about the primitive domain of analytic of shell correlators in string field theory. Please go ahead.
Okay, so first of all, I would like to thank the organizers for giving me this opportunity to present our work. The title of the talk is the primitive domain for analytic off-shell correlators in string field theory, superstring field theory. So this is based on this work written with Ritobroto Bhattacharya, who is a postdoc at CMI. In short, in complex external momenta variables, the Feynman loop diagrams, those with no massless internal propagator in closed superstring field theory are analytic on a domain. This is known from the work of D. Lacroix, Edwin, and Sen from 2018. We'll abbreviate them as LES. We prove an analytic extension of the LES domain to a larger domain. Explicit applications of our formula to 2, 3, and 4-point functions show that the extension equals the well-known primitive domain. I will discuss in a minute which is what is primitive domain. In case of 5-point functions, we do the analysis for limited subcases. So first I will start by posing a question. Then to answer this, we'll discuss our proposed extension and its applications. So yeah. So Green's functions in local quantum field theory, some old results. Starting from two assumptions that the commutator of local operators vanishes outside the light cone, and existence of a complete system of physical states with positive energy. These two put constraints on position space correlators. On the other hand, the official momentum space correlators are defined as the Fourier transforms of the position space correlators, and these constraints on the position space correlators implies the primitive analyticity of official momentum space Green's functions in local quantum field theories, those which are gapped, those without any massless states. So these are standard results, and the primitive analyticity means the analyticity of the official correlators on the primitive domain in complex external momenta, d momenta. So to define the primitive domain, I would be needing this capital Pi for each I as a non-empty proper subset of the first n natural numbers. So for a given I, capital Pi is defined as sum over small pa, a belongs to that set. For example, if I equals to 1 and 3, capital P corresponding to that set will be P1 plus P3. Primitive domain is collection of momenta P1 up to Pn, satisfying two conditions. The first one is the external momentum conservation, due to which primitive domain is a subset of Cn-1d, because out of n momenta, really n-1 of them are independent. The second condition states that for each I, we have to compute the capital Pi and the corresponding imaginary part of it. If it is non-zero, then it must be time-like. And if the imaginary part of capital Pi equals to 0, then the real part is constant, so that in a collision of particles carrying total momentum capital Pi, it cannot produce any multi-particle state. Here, in this relation, Mi is the threshold mass for producing any multi-particle state. So because of this second condition, the primitive domain does not contain on-shell momenta. However, some holomorphic extension of the primitive domain includes on-shell external momenta. Therefore, we can compute physical amplitudes, which are connected amputated on-shell correlators. Furthermore, proper properties of a subregion of the primitive domain implies the crossing symmetry of amplitudes for 2-to-2 scattering, and the analytic extension of the same subregion leads to the Jost-Lehmann-Dyson domain in one particular combination of external momenta, one particular capital Pi, keeping other independent combinations real at the forward light cone. So these results are due to the property of the primitive domain, in particular this subregion, irrespective of the functions that are analytic on it. Now, the enclosed superstring field theory action is directly written in momentum space. It has non-local vertices, and no position space construction is known yet. Now I will be discussing some recent results. So to address the questions that where the Green's functions of cell correlators are defined as a function of external momenta, we have to work directly with the perturbative expansion in momentum space. So we'll be considering any Feynman diagram with n amputated external legs, and only those with which do not contain massless internal propagator. So this type of Feynman diagram will contribute to the infrared shape part of the official correlators. And these Feynman diagrams are analytic on the domain defined by three conditions. This is the result of LES from 2018. So there, the first two conditions are same as the primitive domain conditions, and there is one extra condition. It states that the imaginary part of small pa, whenever non-zero, lies on a 2D Lorentzian plane, means one temporal component and a spatial component. So this type of planes. Because of these third conditions, the LES domain is a proper subset of the primitive domain. However, this is the subregion which used in the proof of crossing symmetry and in the JLD domain. And as I said, that those are the property of the domain, irrespective of the functions that are defined analytic on it. Therefore, for string field theory correlators, which are the functional forms are very different from local quantum field theories, but due to analyticity in this subregion, the proof of crossing symmetry and the JLD domain goes as it is. Furthermore, we will be considering complex Lorentz transformation on each of the momenta, which are matrices whose entries are complex, such that lambda tilde transpose eta lambda tilde equals to eta. And two corollaries from the Elias paper. The first one states that the Feynman diagrams remain analytic at the complex Lorentz transform points whenever P belongs to the Elias domain. And the second corollary states that at each P belongs to the Elias domain, we can allow a small open neighborhood that is at least an epsilon neighborhood where AP remains analytic. So certainly the Elias domain, and due to these two corollaries, Elias domain is can be extended a bit. But the question here we ask is, are the Feynman diagrams analytic on the full primitive domain or not? So this is the outline of our strategy. The starting point will be that the Feynman diagrams are analytic on the extended Elias domain, that is the Elias domain plus two corollaries, and we will not be using any input from the string field, superstring field theory. Rather, it is known that the primitive domain is essentially union of family of tube domains, and this family can be indexed by an index lambda, and tube domains means domains of this form whose real parts are arbitrary, but the imaginary part are constrained in a subset. And here it happens to be a cone in Rn-1D. So because of this triangulation of the primitive domain, inside each of the primitive tube, we identify an open tube from the extended Elias domain, and we will call this open tube as the Elias tube. And we prove the Elias tube admits non-trivial holomorphic extension inside the primitive tube for n greater than or equals to 3 due to Bochner possibly obtaining full of the primitive tube. And we explicitly analyze when n equals to 3, 4, and 5. So now details of this primitive tube. So there is a specific way to divide the space Rn-1 into finite number of cells, and each of which defines a sign valued map, lambda I. So for I as a non-empty proper subset of the first n natural numbers, lambda assigns a sign either +1 or -1, and the primitive tube is defined in equation 1. So these are momenta up to momentum, overall momentum conservation, but the imaginary part of capital Pi for each I either belongs to the forward light cone or in the backward light cone, depending on the lambda function. So really the real parts are arbitrary, but the imaginary parts are constrained in a cone, which we will be calling the base of the primitive tube. And for n equals to 3, the number of cells equals to 6, and each cell gives rise to a lambda function, and each lambda gives rise to a primitive tube. Therefore, the number of primitive tubes is 6, and for n equals to 4, it is 32, n equals to 5, it is 370, etc. Now, to choose, so there is a rule to compute even these lambda functions. So we will be considering S1 up to Sn. These are some parameters, n parameters, subject to this summation, this conservation law. And for each I, we will be defining this capital Si for using this formula. And what we have to do in Rn-1, we will be drawing these planes, Si equals to 0 for all I. And this divides Rn-1 into open convex cones with common apex at the origin. And to be noted that Si equals to 0 and Si complement equals to 0 are the same plane. So each such cone is called a cell, and inside a cell, each of the Si is of definite sign lambda I. So this lambda we will be using. So here I have, in this figure, I have given an example, n equals to 4. And R3 is divided into 32 cells by drawing these planes, Si equals to 0. And one such cell has been marked in this figure. So it is really a 3D cell, but to visualize, I have drawn a surface so that I can mark on a surface. But as can be seen that in this marked cell, S2 plus S3 is of definite sign because S2 plus S3 equals to 0. This mark point lies on some side of this plane there, and inside this cell and each cell, each of the Si is of definite sign, and that is the lambda function. Here I would like to point out that this is something is very special when n equals to 4 or less, that at least n equals to 4, in R3 to define each cell, we need only 3 planes. So specifying the sign of S2 plus S3, S1, and also S1 plus S2, because of this summation conservation, each of the other SI is also of definite sign. I will come back to this point later, but this will be important later. So as I said that inside these lambda functions give rise to primitive tubes, and inside the primitive tube we will find LES tube from the extended LES domain. So LES tubes are union over theta, T lambda theta. Each of T lambda theta are nothing but the primitive tube conditions, but the imaginary part are restricted on a 2D Lorentzian plane P0 P theta, where theta is a set of D minus 2 angles specifying the 2D Lorentzian plane, and in particular theta equals to 0 specifies the P0 P1 plane. So this T lambda theta can be obtained by acting a real rotation on T lambda theta equals to 0. And as we can see that we will be only needing the, we'll not use the first corollary, that is we will not use the all the complex Lorentz transformations, rather we will restrict ourselves to real rotations only. And analyticity of AP in this union is guaranteed by the first corollary because those are obtained by acting real rotations. So this extension, this tube can be, this LES tube can be explicitly written as this, and it is contained in the primitive tube. Although each of the T lambda theta is convex, we prove that this union over this LES tube is non-convex whenever n greater than 2. Furthermore, we prove that this LES tube is path connected, and the LES tube can be thickened in order to make it open, and due to the second corollary. And so to holomorphically extend the LES tube, we can apply the Watson's tube theorem because it satisfies the hypothesis of this theorem, that the theorem states that any open and connected tube has a holomorphic extension to its convex hull, where CH is the smallest convex set containing A, called the convex hull of A. So these are really properties of the domain, and we can holomorphically extend using these theorems, and any functions which are defined in this open connected tube will be analytic on this extended domain. So these we will be using. And as I said that when n greater than equals to greater than 2, greater than equals to 3, this extension is really non-trivial because the convex hull contains new points, because this is union over theta C lambda theta is non-convex. But this is contained in the primitive cone because C lambda is a convex cone containing this LES cone. Because as I said that convex hull is always the smallest convex cone containing the set. So for 3 and 4 point functions, for each of the primitive tube, above extension yields the full of the primitive tube. That is, this equality holds for 5 point functions. We obtain subcases in which we are able to prove this equality. 2 point functions, this is a trivial case because whenever P belongs to a primitive tube, because of this momentum conservation, P1 plus P2 equals to 0, only one of them are independent, and that always lies on some 2D Lorentzian plane. Now these results I will explain in a prototype example. So that is, I will just discuss the 4-point example, 5-point examples, at least the cases we have obtained, and also 3-point example will be just, this is a prototype example. So here there are 32 numbers of primitive tubes. Those are explicitly written here. Of course, there is this momentum conservations, and the imaginary parts belong to the these cones, conical bases, which are explicitly written here. So these are 32 bases, and so for each of these 32 bases, the number of imaginary pi that are required to be in specific light cones equals to 3, because of there are, as I said, that only 3 planes in R3 we need to triangulate R3, the figure I described earlier. And this in turn determines all other imaginary pi to be in specific light cones for each of the base because of this momentum conservation. And because of this momentum conservation, each of the bases are contained in R3D. And out of these 4, only 3 of them are independent. For example, this type of cones written in the first line, we can take PB, PC, and PD as independent. For this type of cone, we can take minus PB, PB plus PC, and PB plus PD as independent. But this change of basis is really an invertible change. But all of these 32 bases can be brought to this common form where Q belongs to C, has 3 capital P, which are to be kept in the forward light cone. So this can be explicitly written as a D by 3 matrix whose columns are in the forward light cone. In this slide, I have given explicitly 3 points from the LES tube, whose convex combination gives this general point Q in the primitive tube. And these Q1, Q2, Q3 are so chosen that each of the columns in Q1 and Q2 and Q3, epsilon is so chosen that they belong to the forward light cone. Furthermore, all the columns in Q1 lie on the plane of P alpha, and all the columns in Q2 lie on the plane of P beta, and all the columns of Q3 lie in the plane of P gamma. So they are restricted in a Lorentzian 2 plane, and really they belong to the LES tubes, and this equality holds. So 5-point functions, the number of primitive tubes are 370. Out of 370, 350 of them, this procedure can be generalized, and this equality also holds. But there are 20 of them for which the bases are given explicitly here. So because of momentum conservation, whenever Q belongs to these conical bases, we'll have 4 independent D momenta, but the number of imaginary PI that are required to be specific in specific light cone equals to 6. So the difficulty arises, and this is generic for, as pointed by Rule, that this is generic for higher point functions as well. And formula to decompose a general Q into terms, each from the LES tube is still missing, but this is an ongoing work in progress. So for this remaining tubes, they can be brought to this common form that 4 momenta are independent, but 6 of them, that P5 and P6, can be written involving using them, and these 6 momenta are in the forward light cone. But what is not fixed here, that Pi minus Pj for points inside this tube can be time-like, null, even space-like. So for points in this tube for which P1 minus P4 is time-like or null, then Q can be decomposed into terms, each of which belongs to the LES tube. And for points for which P1 minus P4 is space-like, what we do, we go to the particular Lorentz frame where the temporal component is 0. And here we are only using real Lorentz transformations, and therefore, to be noted that a Lorentz transformation maps a point in a tube to another point of the same tube, and therefore, without loss of generality for studying analyticity, we can go to this particular Lorentz frame. And this Lorentz frame for these points, the allowed primitive space has 7 parameters, which are S1 up to S6 and L1. S1 up to S6 are because of these 6 capital P belongs to the forward light cone. SR is the PR, the temporal part, minus the Euclidean norm of the spatial momenta, and we know that S1 up to S6 are greater than 0 because they belong to the forward light cone. And there is L1, which is the Euclidean norm of the spatial P1 minus P4 spatial component, and this is greater than equals to 0. And also various inequalities among them can be derived because of this primitive tube condition. So this is the allowed primitive space is really this 7 parameter space, and some set of inequalities among them, along with these inequalities that they are greater than 0 and L1 is greater than equals to 0. Various decompositions of Q into points from the LES tube are found covering various parts of this allowed region. And we are searching any leftover points, if any. And this will be a numerical search. Hopefully, you will be able to report it soon. And now I will give a summary. Oh, okay. Thanks. And now this is the last slide. Now I will summarize and the outlook. So we have extended the LES domain to a larger subset of the primitive domain holomorphically. These are really the property of the domain, irrespective of the functions that are defined on it. Means any function can be defined on the LES domain, extended LES domain can be further extended to this larger subset of the primitive domain. For 2, 3, and 4 point functions in closed superstring field theory, the full primitive domain is recovered. For 5-point functions, analyzed limited subcases and more complete analysis is a work in progress. But really, if our present work can settle the issue of 5-point functions, but rather dealing case by case for all n, we need to automate these analysis in a computer to carry out the proof for arbitrary endpoint functions. I do not know at this stage how to implement this. Superstring amplitudes might have potential singularities on the primitive domain arising from the non-perturbative effects, because our proofs based on the LES results, which states that the LES domain is obtained for the Feynman loop diagrams. Therefore, this is really perturbative. But in non-local quantum field theories, the primitive analyticity proof was for local quantum field theories, the proof was non-perturbative. Certainly, therefore, those are free from these effects, if any. It will be good, interesting to find any differences in the context of analyticity for local and non-local quantum field theories. And the holomorphic envelope, that is the largest analytic extension of the primitive domain, still remains a challenging open problem since Bros, Messier, and Stoda. So really, we did not address the question that what is the full domain of analyticity for the Feynman diagrams. Rather, we asked the question, which is a limited one, that whether they are at least analytic on the primitive domain or not. But to answer this is problem which is open. And thanks for paying your attention.
Okay, so thanks a lot for the nice talk. Are there immediate questions? Otherwise, now we are going to have a discussion session, so there will be plenty of time for questions. Okay, so I see Harold.
Yeah, so I have a question. So when you say for automatizing with a computer, do you have any idea how you would do it? I mean,
at present, I really we have not thought about it, but okay. So there, no. Okay. So answer is no, we haven't. But I think one hope is there that there is a theorem by Kara theory that to know this compute the complex hulls, which we have to compute by a computer for in general endpoint functions. So these new points in the complex hull can be written as a convex combination of at most n minus 1 times d plus 1 points. So there are some bounds that we do not have arbitrary choices of. Here, likely we have for the 4-point case, we have shown that convex combination of 3 points, but in the 5-point case, it was in our paper, it was 4 points whose convex combination reproduced this. But in general, depending upon the dimension, space-time dimension d and endpoint function, there is a bound. I guess that is a hope, but I really do not know how to automate this.
Okay, thanks.
Okay, so I see another Rita Brata. Please.
Yeah, I would just like to make a comment on this thing Harold asked. So basically it will be like for higher point function, it is the strategy to find out all possible decomposition that covers this primitive tubes of domain region. So like what Ratul said, we don't have like an immediate idea as to how we'll go about programming or do an automated like computer program for this. But the general strategy is find all possible decomposition that covers the primitive. So that helps. Kind of.
Okay, thanks for the comment.
Thank you.
So should we continuously now connect to the discussion session, or should we take a 5-minute break? So what is?
Yeah, I guess we can take maybe 2-3 minutes. I mean, 5 minutes.
Okay.
Start just to.
Okay, and then we meet again. Okay.
Okay. So should I stop sharing or?
Yes, perhaps. Okay. So we meet at let's say 6 Central European time, 6 p.m. Central European time.
Thanks.
ADS has rapid states, which depend on the radius, right?
Sorry, there was the sound of recording that I couldn't hear.
Sorry, ADS, I'm just getting back to this, if perturbation theory can hopefully be enough, because ADS has wrapping states, right, which depend on the radius. So how can you possibly see those in perturbation theory?
It depends on which ADS we're talking about. So for example, if you're talking about ADS 3 times S3.
Let's do ADS 5 times S5.
Right. In that case, if the question is about, let's say if you're interested in the string spectrum, we know from the integrability results what the 1/λ expansion looks like. And we know there's the essential singularity at infinite radius, right? But you know, actually now don't quite remember the statement about whether it's Borel-summable or not Borel-summable, but you know.
I'm just asking, I'm not asking about integrability. I'm just asking, there are states that must wrap on the S5, right?
Oh, I'm talking about perturbative string states.
Yeah, but there are other states that you won't be able to see.
It is true there are other states. I'm just restricting. Okay, so to begin with, I'm just considering the weak coupling limit. In that case, there's already a non-trivial question.
No, I'm just asking if the string theory is complete, if you can consider the RNS string theory complete, if it doesn't include these backgrounds.
I'm not claiming to do anything beyond string perturbation theory. The question there was, the question I was trying to address concerning the R flux background is still within the realm of string perturbation theory, of course, because I mean, you know, I mean, within the framework of NSR closed string field theory, the action is to construct the perturbativity in G strings. So that's still just about string perturbation theory.
No, I'm asking a different question. I'm asking if it's a problem with either the formalism of RNS that it cannot describe these backgrounds. So I claim there are some things about these backgrounds that cannot be computed using perturbation theory.
Hold on a second. We need to separate the perturbation theory in R flux versus perturbation theory in G string. Which one are you?
R flux. I'm always talking about.
Oh, but that's not the issue, because I'm talking about so the wrapping states you're talking about are the non-perturbative excitations. The mass go like, you know, one or just.
They depend on G.
Yeah. I'm talking about just perturbative string states. You know, the things that are going to smoothly connect to you know, the usual tower of massive string states in the free string limit in flat space. So those things in ADS 5 times 5 get some correction to their spectrum, right? I mean, in principle, we understand, or at least conjecturally know the answer based on the integrability from N=4 superNOs. But it'd be nice to have a first principle way to access that from the NSR formalism. That's what I was referring to.
Okay, maybe I'm getting confused. Somebody else wants to go ahead. Yeah, go ahead.
Can I think it's really related to Nathan's question, and it's also my confusion. So suppose you start with type 2B on flat space, you construct a closed superstring field theory there. So then you look for classical solutions, and according to you, you take the Ramon-Ramon vertex operator, perhaps plus some web to the graviton also. I mean, you should give web to something, and you're going to search for one parameter family of exact classical solution, let's say an exactly marginal deformation, because this is what you're going to get.
No, this will be, we're not talking about exactly marginal deformation worksheet theory. whenever you can describe a solution as exotic marginal deformation theory, you don't need string field theory, right? I mean, NS deformation are of that type. The Remarkable deformations cannot be described as exotic marginal deformation of the worldsheet CFT.
No, okay, but you're you're going to solve the equation of motion of closed superstring field theory, right?
Order by order in our flux. There's no in principle obstruction.
But you will use the flux as a continuous parameter for the solution. You
Correct.
will use the right.
Correct.
So if you said so, then you would expect somehow that ADS5 plus S5, there is a parameter that when you set it to 0 just becomes flat space. And this is something like
yes,
1 over R.
This parameter is 1 over radius.
1 over R, okay.
Or square root of a prime over R if you wish.
Okay. So
right. I mean, if you worry about the issue of flux quantization, that's not visible in string perturbation theory. When you work perturbing G string, there's no such thing as you will not see the quantization of R flux. Right? That's something you see at finite G string. So in string perturbation theory, you see the automatically the quantization of NSN flux, but you don't see quantization of R flux. That's why this is a consistent prescription. You can solve for this the string field order by order. In fact, we have solved explicitly up to the second order in the ADS3 case. At first order, yes, you will have this marginal R vertex operator. Going to next order, it will not be marginal, as it should be, right? But we can compute them order by order.
I see.
I mean, the ADS5 times S5 is harder than ADS3 times S3.
So you should be able to compute some observable, right? To say that this corresponds to ADS5 plus S5.
Of course. The observables are the string spectrum in the free string limit. That is the observable. I mean, we did that in the ADS3 case at order mu squared. Okay. Everything else was not done. So I mean, there's a lot to do there, but these are completely well-defined observables. And really, this is just in the free string limit. You can go beyond that, but even in the free string limit, there are a ton of very non-trivial questions that can be addressed using this method in principle.
Okay. So in ADS3, you have evidence that the fluctuations around the classic solutions matches with the string spectrum on ADS3.
We did a calculation. In fact, this calculation, you see, is a bit non-trivial because actually there was nothing to match it to because there is no alternative method to access that information in the full quantum regime. So when we did the calculation, that was the first time that one is able to obtain these numbers, period. There was simply no other formalism that allows you to access that data. In the case of ADS3, we turn a little bit of R flux at radius, at string scale radius. Now we checked our answer in some various limits, PP wave limit, we check it against the semi-classical limit, but in the full stringy limit, there was nothing to check it against because there is no alternative method to get the answer. And this was really the only way, as far as I know.
I see. So integrability or this kind of auxiliary techniques that...
No, I mean, in the ADS3 case, I mean, if you are powerful enough to solve the dual CFT, then yes, you will be able to check, but that's not yet, no.
Yes. But do you expect, so coming back to the type 2B case and the ADS5 plus S5, but would you expect some sort of connection between, so you can, let's say, build these solutions that you are talking about, which is, let's say, starts from flat space and builds up ADS5 plus S5, let's say, continuously in 1 over R. And you could also, let's say, run the usual ADS CFT story, right? You put D3 brains and go, you do open closed string field theory on that background. And so there should be a relationship.
As I was alluding to towards the last bit of my talk, I think we'll have difficulty. So you might say that, why don't we use the logic of string field theory to try to improve ADS CFT as a derivation beyond the supergravity limit? I would say the problem of that is, so first of all, philosophically, one should not think of the string field theory as an improved version of GR or low energy effective theory, because they're really on very different footing. There's no beauty in general coordinate invariance in string field theory. In particular, I do not know how to take a near horizon limit in the language of string field theory.
Mm-hmm.
Right. So that to me is a real problem. So I don't know. I wouldn't know how to. So I certainly can't imagine solving, perturbatively the solution of of the black three brain in string field theory, but I wouldn't know I guess the thing is that I wouldn't know how to even see the existence of the horizon in the string field theory language. Because in string field theory, we always describe a solution as deformation from the fixed background. So we start with the flat space and we deform, we turn out some. I mean, it's not like you can just change to a different coordinate system and see that okay, there's a near horizon throat. That I don't know how to do in string field theory, right? I mean, there's no such prescription. So without the prescription, there's no formula that allows you to take the near horizon limit. It's really on a different footing from the low energy effective description.
Yeah, so I think I agree with you. So I think we just see the problem from two different aspects. So you see the problem is having to do with this not being able to describe these backgrounds, and for me, I just described it in a different way, but it's the same problem. I think that string field theory at the moment is inadequate.
Nathan, I think I'm restricting myself to a more modest set of questions. Let's say I just want to. I just want to study, let's say, I just want to study things like perturbative string spectrum or perturbative string scattering amplitudes, but in a fully stringy ADS.
Well, never Schwartz backgrounds. I agree with you. I mean, I understand, and we don't know how to do it around other backgrounds. That's all. But that's all I'm saying.
No. Sorry, there's two separate questions. Because there's the two expansions. One expansion R flux, the other is the expansion in G string. I think we have to separate the two. I don't think.
Sorry, no, I disagree. G string is an artifact of string theory. In supergravity, there's no distinction between a Ramon background and a Schwartz background. That's an artifact of string theory. It's not an artifact of physics.
I didn't say it's an artifact, but that's why I didn't think that there was such a dramatic claim to say that the string field theory allowed to access.
That's what I say is a problem. Theory. It's not a problem with supergravity. It's a problem with string theory.
Well, I didn't say this is a problem with supergravity.
Right. So that's what I'm saying. So string theory has this feature, which is a problem, which is not a problem, for example, general relativity or supergravity. Or
but there are unambiguous physical observables that we care about, which is things like the string spectrum in the free string limit.
We would like to have a description which can describe any background of supergravity. We would like to have it. We don't have it.
That was not the question I was posing. That was not the objective. My objective was a very modest one.
I understand. I'm just saying that I think that's a problem with string theory, the way it's formulated at the moment.
I mean, surely I agree that the string field theory is not some magic wand. It doesn't do even what the low energy effective theory does.
Okay, I don't think we're gonna agree, but I think you said earlier the same thing that I was intending to say, which is that we don't know how to. The string theory has this limitation.
I'm certainly not claiming the closed string field theory is a non-perturbative definition of string theory. I'm not trying to say that.
Okay.
All I'm just saying is that it allows us to address a limited set of questions. But nonetheless, those questions were not accessible using conventional on-shell methods, at least in NSR formalism.
Okay.
That's all I'm saying.
Okay, I think we agree on that.
Maybe the difference is what Nathan wants is one formulation which solves everything. And I think that's not what we are really looking for. I mean, okay, at least that's not what string field theory is supposed to be. And we don't have any such formulation, right? But as long as we have different formulations which you can piece together to solve the problems that you want, that should be good enough, right?
Right, but I don't think we have that yet. So for supergravity,
no, we don't have that yet. I agree. So it's just you add more tools to solve some more set of problems that you couldn't solve otherwise.
Yeah.
I think that's the way one should think of string field theory or any aspect of string theory as such.
Yeah, which is, I think, unfortunate. I mean, it would be nice to have one formulation which we could use for different backgrounds. We wouldn't have to piece things together from supergravity and string theory and things like that.
Yeah, I agree. On the other hand, if from the practical point of view, if we have formalism to address any question that you want, maybe using different tools, I would think that's from the practical point of view, that's also good enough, right?
Yeah, it depends how you define practical, but okay. I mean, if you want to go, you want to say that you have a formulation which you can apply in different backgrounds, and of course, the methods you use, you can depend on the background, but I would like to have a formulation which can just as easily describe ADS5 times S5 as describe Nevers-Schwarz spectrum.
Yeah, I mean, it will be nice to have such thing, but if we don't, but if we have separate tools for each of these, I would think okay, that's maybe not the best solution, but it's good enough solution, right?
Okay. Yeah, I guess it depends what you want, but
yeah.
Andrei? Oh,
can you hear me?
Yeah.
I have a question to Ashok. Those free fields which decouple from string field theory action, what happens if you start not in flat space, but in a curved target space? Will they feel gravitational field?
Yeah, I think as long as you start with a CFT, where you can formulate string field theory, this construction goes through. You don't have to start with flat space, but you have to start with the background which solves classical string equations.
So they feel physical fields, but there is no back reaction. Is that the claim? They feel, for example, gravitational field. If you put your in curved background, then this will be free field equations in a curved background, right?
That's right. Yes, exactly. Yeah.
But there is no back reaction.
No, there is no back reaction. Yeah. Because this formalism that I described, I didn't specify what was the underlying CFT based on which you calculate these correlation functions. So any background is good enough.
I see. Thank you.
I see. So these free fields are not necessarily in flat space. It depends on the background CFT.
That's right. Yes. It's free in the sense that it has quadratic action and then it doesn't back react on the interacting part of the theory.
So if there are no other urgent questions, I have a small question for Minjae Cho. Is he here?
Oh, yes, I'm here. Yeah.
Hi. Yeah. So so the nice computation you have shown today. In fact, essentially, let's say the same computation, but in a sort of different way, was done many years ago by Nathan Berkowitz and Martin Schnabel, where they computed the quartic potential of Yang Mills. And so your result is essentially how to say a corollary, right, of that when you just go on the abelian part of Yang Mills, let's say, when you just have one d instanton and not n. And okay, so this was computed in Witten theory, in fact. So in this superstring field theory in large Hilbert space based on Witten products, which is a very peculiar realization of the vertices you have used. So your computation is, let's say, valid for, I mean, it's very general, but already there, in fact, this theory has a cubic interaction and has also a quartic interaction. And in fact, if you go and look at this computation, you can realize precisely that the role of the quartic interaction was precisely to give the vertical integration that you were talking about, because the Witten vertex, yeah, because the Witten vertex integrates over all bosonic moduli space, right? Just with propagators, and you don't need the vertices to do this. But still, you have to adjust the pictures, right? Because you get the S channel and the T channel with different picture assignments, and then you need this quartic vertex that doesn't integrate anything in the bosonic moduli space, and it only integrates in fermionic moduli space. Let's say this does this vertical integration. Okay, so okay, but this was not okay. So the other thing is that then, based on that computation, many years later, with a student, I revisited that computation, and in fact found out that this computation completely localizes at the boundary of the worksheet moduli space, and in fact so what I'm saying is that you should be able to find zero for this coupling, not really computing a 4-point function and showing that this is zero, but just so you should be able to play with the picture assignment and show essentially that the full amplitudes is almost BRST trivial, except for a singular point at the boundary of modular space that gives you the full contribution. And in this case, the full contribution will be zero, okay? Because this full contribution in general is the field strength itself at zero momentum. And yeah, so I was just, I imagine that you can look at your computation playing with the picture assignment and show that this is zero without actually computing it based on these results.
So actually, I was not aware of the first reference that you were talking about. So was that in the context of the deep brains or the instanton?
Oh, it was in the context, let's say, of deep brains, but the computation was done at zero momentum, so it is valid for administration. It's a
and it was also in the
momentum
superstring context, you say?
Yeah. It's a genuine zero momentum computation, so it's valid for any, yeah.
I see.
Can I make a comment regarding this? In my view, the purpose of Minjae's, the calculation Minjae presented is not about the answer. It's very easy to prove that the answer is zero without doing all that calculation, because we know that for this computation, the integrand is a closed form on this fiber bundle that's being integrated. So you're free to deform contour, and you can just choose a deform to a convenient contour as how we usually do the on-shot calculations. I would say the purpose of the exercise is not so much to show the answer is zero. That's very easy to get. The purpose of the exercise is to show that in this scheme of calculation, all the pieces involved are manifestly finite. In particular, it's a check that Sen's gauge works. I would say that that's really the purpose of this computation. To get the answer zero is very easy.
No, I'm just saying that this Witten theory is just another example in which this computation is finite and every term is finite. As you say, there are no divergences at any point in the computation. It's just another realization of other vertices. And in fact, it is let's say it is special for one particular reason. And the reason is that this particular vertex that Witten uses, which is left-right symmetric, doesn't give rise to this extra complication that Ashoke is talking about these extra zero modes in the kernel of L0, which is given by these del C fields. So that's kind of a miracle of the Witten vertex that if you compute the star product of two moduli that Minjae was computing about, you never generate this extra field. So at that time we didn't see that field. I don't know if what I'm saying is clear. I'm just saying that it's yeah.
In this Witten vortex, there used to be problems with collision of picture changing operators, right? Because he had the picture changing operator at the midpoint.
No. Yes, I'm saying Witten vertex, but I'm considering the theory that Nathan wrote down, the Wezumino-Witten-like theory that doesn't any insertion of picture changing operators. Okay. Yeah. And if you want, there is the parent of this theory, which is the Munich theory that is obtained via partial gauge fixing and Firat definitions. Okay. So both of these theories are based on Witten vertex, but they have explicit quartic coupling, whose role is precisely that of adjusting the picture by going from the S channel to the T channel, which is essentially vertical integration. Okay, because you cover all moduli space. I mean, half of it with the S channel, half of it with the T channel, but then you have mismatch of picture assignment, and you have to correct it with the quartic vertex, which is precisely the vertical integration.
Okay, so in that formalism, I guess this extra field has been integrated out.
Yes, so in that case, the extra field that is not there essentially. So it's not produced in the propagator, and so you don't have to integrate it out essentially.
Okay, meaning it's already part of the vortex, definition of the vortex, presumably.
Yeah. But it's kind of a miracle of the Witten vertex, which is based on the symmetric OPE, and therefore you cannot create a del C.
Okay. Yeah, I guess even in bosonic string theory, that's what happens, right? That
even in bosonic string theory, yeah. So in fact, in bosonic string theory, you reproduce it just some S channel and T channel, and then so then you don't need a quartic vertex because there is no need for vertical integration.
Yeah.
So I would guess that then, like, local chart-wise, basically we know that Witten's vertex covers everything. So all the higher vertices, if one ever needs to talk about them, their role is to literally check that PCOs are not like, gapped from each other. So it like gives the continuous like cover in a sense.
Sorry, was this a comment, a question, or?
Oh, no. I was just asking, like, because, typically my previous understanding was that Witten's vertex has like problems with putting PCOs. You're saying that higher vertices can actually serve to get rid of that problem.
Yeah, so there are these open superstring field theory which are based on Witten vertex, but that doesn't mean that they are cubic. Okay, so it just means that it has a cubic vertex. I mean, it has a cubic coupling, the quartic coupling, quintic coupling. So they're based on homotopy algebras. But if you look at the higher point vertices, you see that they don't integrate on bosonic moduli at all. So and they are so these extra vertices are essentially there to rearrange the position of the picture changing operator in such a way that the all moduli space is covered in a continuous way. And so in that sense they are the vertical integration, these extra vertices.
So are these only for classical open string field theory, or is there open closed version of this story?
I think open closed version is not. Yes, I'm at the moment working with the Jakub Vožmera to extend some of the results to open closed string field theory. Essentially, these results about localization. So the fact that there are some couplings like the one that you computed today, that you don't need to know these. I mean, what happens in the interior of the moduli space because they localize at the boundary of moduli space. And so these things are very generic. They happen also in closed string field theory. So we saw. So Ashoke was the first one actually who discovered this mechanism in heterotic string theory, and then we discovered it also in other versions of string field theories, and so on and so forth. So I am sure this kind of things also works for open closed string field theory, and
Yeah, because when we are doing this closed string computation, we actually are working with open closed. And I mean, even though we are not talking about propagating closed string degrees of freedom, we are actually working in the open closed setup, and using sense gauge is giving like non-trivial contributions in many of the parts of the computations.
I can definitely imagine this.
Yeah. And again, like the computation that I presented today was merely a toy exercise for this more complicated problem for like involving closed string. So I was wondering if the version of string field theory.
For the closed strings, so if your closed strings are allowed to have external momenta, that is what typically happens, right, in backgrounds. Then you can use Witten theory with these open closed vertices, these Elwood invariants. And this is like, say, a sort of toy version of open closed string field theory. And so this is going to give you amplitudes, at least, let's say, these amplitudes that are okay.
Yeah, in fact, even in open closed string field theory, it is sometimes possible to choose the vortices so that the contribution from this extra state just goes away in the intermediate state. I mean, in fact, if you remember, I mean, the calculation that I did for this 2-point function, when it factorizes into an intermediate open string channel, the particular choice I made was designed so that the extra contribution goes away. This zero on the vacuum contributions. Right?
Yeah.
So I think for low point diagrams, you can probably adjust the vertices to get rid of some of these diagrams.
Yeah, yeah.
But once they start propagating in the loop, I think it's very hard to get rid of them.
Yeah, and okay, so.
Yeah, thanks for the comment, by the way.
Yeah, I think it would be interesting to I mean, so your treatment was very general and to see how, I mean, how your computation is implemented in a sense, in a sort of automatic way in these already existing theories that are based on Witten product. Because this Witten product is somehow special, right? And yeah.
So Carlo, I would think that just having Witten vortex is probably not enough to get rid of these extra diagrams, because you have to also choose the PCOs symmetrically, right?
Probably, I guess so. Yes. So this okay. So according to my experience, this happens in this Wezumino-Witten theory that is in the large Hilbert space, where you just don't have these picture changing operators. And this happens also in this Munich theory, where these picture changing are very wisely chosen in such a way that everything is cyclic and symmetric.
Okay. But is this, yeah, cyclically symmetric is good enough for twist symmetry? Because here I think the twist is
okay.
Right?
Yeah, so I think so. What we saw was that for the choice of let's say X naught, let's say just use X naught. So this Munich theory, you can distribute the picture changing operator basically in the way you want. I think you need some sort of symmetry condition, but for sure you can use X naught.
Yeah, I think X naught will probably work.
Yeah.
But my feeling is that you
so
probably have to
them,
put some condition for these 3 cubic couplings to go away.
Probably, yes, yeah. Okay, I'm not sure. Perhaps if Ted would be here, I mean, he could answer. I don't know if there can be some subtleties. For sure, for the choice of X naught, which was the choice that we have always used to do these computations, we know that you never generate this extra field in quartic vertices. Then, to me, it's still not clear. If in higher point vertices you will never generate it, or yes, it's not completely clear to me. But anyway, if you're going to use this, let's say, Witten-like theory, if you're going to compute loop amplitudes, then this thing I think will propagate. I mean, anyway, so because there is no way that you can get rid of it in loops. So you will have to. Yeah.
Can I ask a question as well?
Please.
Can you hear me? So
yes.
I was wondering, the requirement for vertical integration, is that at all associated to the presence of super curvature that can't be gotten rid of globally? It's a general question. I don't know if someone wants to have some comment.
When it came from the idea that you may not be able to choose the section continuously, right?
Yes,
but as I said, it's not proven that it is not possible to do it.
Yes, but
right?
Is there any reason to believe that it might be associated to it might be necessary in the cases when the supercurvature is non-trivial globally.
Probably because it's like a global abstraction. So I would think that it's related to,
yes,
yeah, the supercurvature being non-trivial.
Okay, yes.
But I don't know how to make this connection more direct.
Okay. I guess, I mean, is there a way to know when the supercurvature, so we have the Euler number, the Euler characteristic, and we can compute that for a general, any Riemann surface, any super Riemann surface. But in some sense, that gives the integrated supercurvature as opposed to the supercurvature. I don't know if, is there some relation between the Euler number being non-trivial and the requirement for vertical integration? Is there some link between these two?
No, not that one knows of. I mean, I think, as I said, I mean, whether you need vertical integration itself is not, has not been established, right? It could be that there's a clever choice by which you can avoid vertical integration.
Yes, I'm just wondering if it's known when it's actually required.
No, it's not known. That's the point.
Okay.
It's not even known if it's required, right?
Okay, I see.
So
yeah, I mean, okay.
So it doesn't.
Okay.
It doesn't
But
arise.
required in the PCO formalism, I guess.
No, even there, even in PCO formalism, it's not proven that it is required.
Okay.
Right?
What has?
I mean, what one knows is that there are these spurious singularities, and the easiest way to avoid them is to do vertical integration. But
okay,
as Kate has been emphasizing for a long time, it's not known that it is actually required.
Okay. So it might even be possible to construct sections, global sections, even in the PCO formalism without vertical integration.
Yeah. It's just that the spurious poles are so little understood. I mean, you have a very complicated equation to determine the location of the spurious pole. And so whether it's possible to find global sections, avoiding those is very hard to analyze.
I see.
So is there a way to understand physically these spurious poles, right? So they are not just the collision of picture changing operators, right? Because they arise at finite distance, right? So when there is no collision in general. So
yeah, I think the physical way to understand is that they are breakdown of gauge choice. That you are choosing these delta function gravity nodes, and you can show that precisely at the location of the picture changing operators, that gauge choice is singular.
Oh, I see. You mean the gauge choice for the gravitino?
Yeah, gauge choice for the gravitino. Exactly.
Okay. I see.
Just let me ask, in that sense, I should suppose you have a Riemann surface and there's 5 PCOs that are moving around. So you have 2 real parameters describing the position. What is the dimension of the singular set?
It's always codimension 2, real codimension 2.
Real
codimension. Complex codimension 1.
I see. And nobody has characterized them in some.
Meaning, we know the equation which determines them.
Right.
But there is really no good understanding of the topology of these spaces. And of course, this includes when the operators collide. Right? That's a trivial singularity, which you can easily see.
Okay.
But the ones which are difficult to manage are the ones which are not of that kind.
Can you understand the space in the neighborhood of a collision? Like, is it
But in the neighborhood of the collision, you can always try to go around because it's codimension 2, right?
Yeah. Oh. Well, the collision, you said the set of singular configurations is codimension 2. So one singular configuration is a collision, but there are singular configurations that, so suppose they collide, is there a way to understand how you can separate them and keep being singular? Is it this singular space is a connected space? Is it
yeah, I think it's a connected space. I mean, at least it's a each collision is like a connected space, because it's like you are putting one equation on variables, right? X1 equal to Z1 equal to Z2.
Yeah.
If these are the locations of the PCOs, right? And each of these ZIs are varying as a function of the moduli. And so how you choose the ZIs is up to you, right? So the idea is that as you vary the moduli, can you move the ZIs in such a way they avoid collision? Right? I think locally you can always do it. It's a question of whether globally you can achieve this.
Nice.
Because it's up to you to choose the ZIs, right? So you can always decide that in any given patch, you can always keep them separate.
Yes.
Right, and that's what we use. That I mean, if you divide up the moduli space into, if you do triangulation of the moduli space, then inside each triangle, you can always choose the PCO so that they avoid spurious singularities.
Yeah.
Right, and then we said that at the boundary, you do this vertical integration because you don't demand that they match across the boundary. But we didn't prove that it is impossible to match them across the boundary. Right, I think that's the question of whether you need vertical integration or not. Because if you could match them at the boundary, then you wouldn't need vertical integration.
So which is the simplest example where this problem arises? Which amplitude, which moduli space? Like,
I think even at the tree level, if you have, if you need two PCOs, you already have an issue, right? That you have to make sure that you can always keep them separate. But so it's like this. Suppose you have a 4-point function of NS vertex operators, NS vertex operators.
Okay.
Right. So it's each has -1, say -2, and then you need some PCOs to compensate for the picture changing, compensate for the picture number, and you have to move them around as you are integrating over the moduli, right? There is one complex moduli, right? Because it's a 4-point function on the sphere.
Yeah.
So you have a 2-dimensional integral, and as you do the 2-dimensional integral, you have to make sure that the PCOs are moving around, so that they avoid each other, they avoid collision with each other.
Now that avoidance must be pretty simple because I would imagine.
Well, you have to avoid collision with each other and with the vertex operators.
Right. But still, that seems like you understand those diagrams very concretely, the moduli space of fairly well. And but you say in this case, there's configurations that look regular, but are really singular?
No, not in this case. In this case, everything is explicit, right? See, you either have to, either the picture changing operators have to collide, or they have to collide with the vertex operator.
Okay.
But you cannot keep them fixed in the plane, because as you integrate the vertex operator, sometimes the vertex operator will approach a PCO location, right?
Right.
So you have to move them.
Yes.
And as you do, you have to make sure that you can do this over the entire integration plane of the vertex operators. Right?
Right.
And at the same time, it shouldn't collide with another PCO.
Yes.
So I think in this case, one can argue that you can achieve it, but you still have to do a little more work. It's not absolutely obvious to me that.
Okay. Yeah, I would have imagined that it's kind of simple to avoid them, but maybe it's a little, you have to do it with some care. But so which is the simplest case where there are singularities that don't correspond to collisions?
On the torus.
Torus, so how many 2 picture changings on the torus?
Yeah, I think even with 1 picture changing, you will have this problem. If you have, say, on the torus, suppose you had 2 Ramond vertex operator.
Yes.
It still requires 2. I mean, yeah, I think any non-trivial amplitude on the torus probably will require 2.
2 picture changes or 2?
Let me think. I think maybe if you have a, suppose you have a 1-point function of minus half picture Ramond vertex operator.
Okay.
Then you need only 1
PCO.
Yeah, I think you need only 1 PCO. Except that I have a feeling that this probably just vanishes.
Oh.
Because it will be hard to conserve picture number in the left and right separately.
Oh.
Yeah, so I think the simplest amplitudes on the torus will require 2 PCOs.
2 pictures and 1 external state, say, or?
Maybe this is a good example. Take a -1 picture, Nebuchadnezzar's vertex operator, and 2 PCOs, but 1 holomorphic, 1 anti-holomorphic. Okay, so they will not talk to each other.
2 PCOs.
Yeah, 2 PCOs, 1 holomorphic, 1 anti-holomorphic. So in the holomorphic sector, you really have 1 vertex operator and 1 PCO.
Right.
And I think that already has this extra spurious poles.
But in that case, this extra spurious pole is really a point, right? Or a collection of points, maybe?
It's a point, yes, I think so, because it's codimension 2.
Right.
Yeah.
So I was wondering if it is maybe easy to pass around it. Maybe not, but.
Yeah, maybe in that case, it is possible to pass around it. Yeah. But I think Bartona's example looking for an example where you first see this unusual kind of thing.
Yeah.
Sure.
Yeah, and then you have to worry about whether you can pass around it. Yeah.
Sure.
Right.
I think this Donaghy-Witten paper, that establishes that you cannot choose holomorphic sections, that you cannot let these PCO locations very holomorphic. I think that's what they rule out explicitly. But whether you can, that once you allow non-holomorphic dependent, allow non-holomorphic functions, whether you can still avoid it, it's not clear.
I see. Wow.
But I think a part of the virtue of the vertical integration is just that you don't have to worry about the complication of topology of this fiber bundle with the PCO location.
Yeah, exactly. Yeah.
You can just, I mean, if you want to maybe not give the most elegant formula, but if you want to compute numerically some scattering amplitude, you just scale the modular space and patch up and add the vertical integration pieces, and you get a numerical answer.
But wasn't it the question that even the vertical integration can hit the singular space?
Yeah, it certainly does. But vertical integration precisely avoids it by the fact that you really need the difference between the endpoints.
Oh.
So even if it hits the singularity in between, it doesn't matter. Because you are not actually doing the integral. Right? If you actually do the integral, you may pass to the singularity, but because it's the difference between the two endpoints,
okay,
you get a finite answer.
See.
Yeah, and also I think the vertical integration is useful because often I have found that even if you can do it by continuous variation, it's easier to do the vertical jump. That you choose the PCO. I mean, exactly like what Minjae described, right? That
Exactly. Yeah.
Yeah.
It's pretty cumbersome to actually choose. I mean, in the disk case, you don't need vertical integration. You can just make it continuous. But if you do that, the computation becomes quite cumbersome. And that's the reason why we just chose to do vertical integration for the convenience of computation. And it actually helps in practice.
Exactly, yeah.
Let's see.
In fact, this localization that Carlo was talking about, I think is, basically uses this fact, right? That you make a wrong choice of feature number of the vertex operators, where the answer is 0. And then you calculate the difference by vertical integration, right?
Yes. It is exactly this. Yes. Yeah. So the whole amplitude is essentially a boundary term, and so you add a vanishing term that vanishes because of some charge conservations, and then you can write the sum of these two things as a total derivative.
Yeah.
And then
Can I ask something unrelated?
Please.
So I want to follow up a bit about the thing I asked at the end of Kasia's talk about this boundary CFT from string field theory. To me, the approach is quite funny because usually we think of the boundary CFT something that's the string theory knows in its free limit already. Right. Whereas the string field theory solutions that one considers in this context relies in a crucial way on the interaction. So it seems that there's a lot of redundancy that was put in here. I was wondering whether there's some, because I think a number of people here has worked on this problem. I wonder if there's some way to kind of isolate what that's actually needed and get rid of all this string field theory ghost junk. It doesn't seem to be, it should not really be logically necessary, but somehow is a useful technical tool. I mean, for example, if you consider the most trivial RG flow, which does absolutely nothing, that is, you deform the CFT, the boundary CFT by the identity operator, the corresponding string field theory solution is Schnabel's solution. So that's already very complicated, but it corresponds to a completely trivial flow. So, what exactly is going on here? Maybe I was wondering if someone can illuminate me on this.
So if Martin is here, perhaps he can say something. So Martin looks like he's here, but I'm not sure he's hearing us. Yeah. So if Martin is not here, maybe I can try to say something. But I mean, my point of view is that I don't know what's happened. It's like a black box. These level truncations find solutions that sometimes are not seen in usual RG flows. So one of the things that sort of convinced us in, let's say, in the community, that sometimes string field theory is more powerful than usual, let's say, CFT methods, is precisely this fact that sometimes you can find solutions corresponding to boundary states that have higher G functions than the one that you start with. Therefore, you know that these are not going to be connected by RG flow. So you find something, yeah. So let's say the extremal example is like finding a two-brain solutions in the string field theory of a one-brain solution, of a single one brain, right? So there is no operation, there is no boundary deformation that you can do on the worksheet that is going to give you such a thing. It's like a very irrelevant deformation. But the string field theory solution can see it. So in a sense, it looks like it's more powerful. But why? But you are asking me why, and the reason, I tell you, I don't know. But maybe here there is someone that can say something more about it.
And this context of string field theory only knows about the endpoint of RG flow, right? It doesn't know about the flow itself, it seems.
Yeah, this is also looks like it is, yeah. But I can tell you more than this. It looks like a hell to construct a solution that is based on the RG flow. So this was, so we tried very hard to build, it's a kind of very natural question, right? So you have a relevant operator on the boundary. You would like to find a solution that follows the flow of these relevant operators and goes down to the IR fixed point, okay? So it turns out that this picture can be. So the only example which I know in which this thing really works in a completely neat way is the tachyon vacuum. Is the boundary RG flow driven by just the identity operator, which gives in fact a Schnabel solution or something age equivalent to it. But if you just start with a generic relevant field on the boundary, and then you try to build something that looks like roughly the Schnabel solution that excites this relevant field and somehow. So you see that it's very difficult to solve the equation of motion, and you run into sort of unsurmountable problems. So this is kind of still an open question of how to find. Given a relevant field, how to write down the string field theory solution that corresponds to the IR fixed point of that relevant field.
So purely in the RG context, as far as I know, we don't know how to define the notion of Wilsonian effective action in conformal perturbation theory. And also we don't really know a useful way to define the notion of a renormalized coupling in conformal perturbation theory beyond leading orders. Because it's kind of hard to choose a scheme to just define this. This feels like a kind of technical issue, but in practice, it just seems to be difficult to do. I guess I was wondering whether the string field theory approach can actually shed light on that. You can maybe use some particular components of the string field solution to define the notion of the renormalized coupling. But I guess if it doesn't capture the entire flow, it only knows about endpoint, maybe that's not so clear. Anyway, I find this curious.
Yeah, it's quite mysterious, I would say, but yeah. Okay, so there are no other questions. Perhaps we can stop the session, and I ask the organizers what to do.
Yeah, I think if there is another question, we can stop here. So in any case, we have another session tomorrow from 7 to 8 in US time. So it's like 1 p.m. to 2 p.m. I think in Europe for people who want. So again, it's completely as you can. And tomorrow it's more informal, so like the morning session we will not record anything. And I remind again that we have Zuib for people who want to chat offline and not like asynchronously. And so I would like to thank all the speakers of today who are still there, and especially Carlo and Yuji for sharing the sessions. So thanks
See you.
everyone.
Thanks, Harold. Thanks.
See you tomorrow.
Good.